The James Webb Space Telescope is looking deeper into space than any other telescope ever made. But what it sees doesn't make sense. Images from galaxies more than 13 billion light-years away have shown structures that look fully grown, big and bright, as if they had already gone through billions of years of change. What's wrong? Every model of the universe says that none of that should have been possible in that amount of time. It looks like these galaxies have been around longer than the universe itself, longer than the Big Bang. If that's true, then what we call the start of everything may have been just a new start for something much older that can still be heard in the light Webb just caught. The discovery that shouldn't exist. Astronomers thought that the James Webb Space Telescope's deep field image would show faint, primitive galaxies, like tiny groups of new stars still glowing in hydrogen haze when NASA first shared it. Webb instead showed something that even experienced cosmologists couldn't explain. There were galaxies all over those deep fields that were too bright, too big, and too well put together to have formed just a few 100 million years after the universe was thought to have started. One galaxy, named Glass Z13, looked like it was formed only 320 million years after the Big Bang. In cosmic words, that's only a heartbeat after time began. But there were already billions of stars in it. These weren't small, chaotic smudges of gas like the early universe simulations predicted. Many had defined shapes, stable disks, and heavy elements that required multiple generations of stars to create. Their light, stretched across more than 13 billion light-years, carried chemical fingerprints that told a shocking story. They had already evolved. That means these galaxies didn't just form fast. They formed impossibly fast. According to the standard lambda cold dark matter (LCDM) model, that shouldn't be possible. Webb's instruments, especially the near-infrared camera (NIRCam) and near-infrared spectrograph (NIRSpec), allow astronomers to detect galaxies with redshifts, essentially measures of how much the universe's expansion has stretched their light, above z equals sine 12 or even z equals sine 14. Each increment in redshift is a leap backward in time. By z equals sine 13, you're looking at light emitted when the universe was barely 2% of its current age. The problem is that, at that point, there shouldn't have been enough raw material, time, or gravitational clumping to produce galaxies that are massive or organized. At first, many scientists assumed these must be errors. Perhaps Webb's instruments were misreading light from closer galaxies, hidden behind clouds of cosmic dust. Or maybe gravitational lensing, the bending of light by massive objects, was magnifying distant specks into apparent giants. But repeated spectral analyses didn't agree. When the JADE West Advanced Deep Extragalactic Survey team checked again, they found the same thing. Real galaxies, confirmed by multiple instruments, existing when the universe was supposedly still assembling hydrogen atoms. Researchers compared Webb's observations with earlier Hubble data. Hubble, powerful as it was, could only see a fraction of the faint red light these galaxies emitted. Webb's infrared sensors cut through that limitation, giving scientists direct spectra instead of inferred guesses. The result was unambiguous. The stars inside these galaxies were older and heavier than expected. Some showed elements like carbon and oxygen that take generations of stellar death to forge. It's as if the universe had skipped its childhood and jumped straight into adulthood. This is what made astronomers like Dr. Emma Curtis Lake of the University of Hertfordshire remark, "We might be looking at something we don't yet understand." If these galaxies truly formed within a few 100 million years after the Big Bang, then the entire timeline of cosmic evolution, from the formation of the first atoms to the ignition of the first stars, has to be compressed by factors of 10 or more. It means the universe built itself faster, denser, and earlier than any model allows. If matter organized that quickly, perhaps cosmic inflation, the rapid expansion thought to have followed the Big Bang, ended sooner or proceeded differently. Or perhaps the Big Bang wasn't the singular beginning we've always believed, but just the latest in a cycle of cosmic rebirths, each leaving behind residues of structure and matter that seeded the next. Some cosmologists have even suggested that what Webb is detecting could be remnants from a previous universe, galaxies that somehow survived a big bounce or a transitional event before our own cosmic dawn. Even the most conservative theory is still strange. The clock in the universe might be off. The Hubble constant is the rate at which the universe is expanding. If it is slightly different from what we think it is, the universe could be older than we think. This would give those early galaxies more time to grow. However, every change makes other parts of the model contradictory. In case you change the numbers too much, the cosmic microwave background will no longer fit. The galaxies shouldn't exist if you leave them where they are. In either case, something important doesn't make sense. Redshift beyond the edge. Each picture that the James Webb Space Telescope takes in deep space is more than just a picture, it's a time clock. Each speck is made up of light that has been traveling through the universe for billions of years. Astronomers use a number called redshift, which is written as Z, to measure this stretch. The redshift number tells you how far away and how old an item is. The record for the farthest distance in space stayed around Z = 11 for decades. This means that the light came from about 400 million years after the Big Bang. That record didn't just fall though, Webb broke it. Scientists started to confirm candidates whose Z values were higher than 13, 14, and maybe even 20. To grasp why that's extraordinary, it helps to understand what redshift means in practice. When the universe expands, light waves traveling through it are stretched like marks on an inflating balloon. The longer those waves become, the redder they appear. Astronomers can read this stretch factor directly from a galaxy's spectrum, the pattern of its elemental fingerprints. Each known element has precise emission lines. If those lines are shifted toward red by a measurable amount, we can calculate how much space itself has expanded since the light left its source. In other words, redshift is not just distance, it's cosmic time dilation written in color. But Webb has forced scientists to consider whether that color coding might be telling a more complicated story. Objects with Z above 15 appear to come from an era when the universe was less than 250 million years old. According to the LCDM model, that's before the first stars could have even ignited. Yet Webb's data show luminous, structured galaxies already emitting heavy element spectra. Clear evidence of earlier generations of stellar activity. The math doesn't fit. To reach those distances, the light would have had to travel through space that didn't yet exist when the Big Bang supposedly occurred. There are two broad ways to interpret this. Either our measurement of redshift is being distorted by new physics, or our timeline of cosmic history is incomplete. The first possibility suggests phenomena like gravitational redshift or exotic dust absorption might be mimicking extremely old light. However, Webb's multi-filter imaging was designed to guard against that. Each object's redshift is cross-verified using spectroscopy, separating light into fine spectral lines that can't be faked by lensing or local interference. In several confirmed cases, such as galaxy candidates Sears 93316 and Jade's GSZ 140, the spectral signatures leave little doubt. These galaxies really do lie beyond the redshift limit that standard cosmology can comfortably explain. If that's true, then a deep truth follows. Another name for the Hubble constant is the rate at which the universe is expanding. It may not be constant at all. Small changes in its number can cause the age of the world to change by hundreds of millions of years. The so-called Hubble tension is already showing up in some studies that use supernovae and Cepheid variables to find differences. That strain is pushed to the limit by Webb's findings. If the world grew faster than we thought in the beginning, structures might have been able to form faster. But that same change throws off the age that can be found in the cosmic microwave background, which is still one of the most accurately recorded things in physics. As soon as you fix one problem, two more show up. We could be looking at light from a hidden epoch, which is a time between the Big Bang and recombination. During this time, leftover photons from an earlier cosmic cycle may have mixed with ours. Then, redshift wouldn't be measuring growth from a single starting point, but from the histories of many cosmic times that overlap. That hasn't been proven yet, but the spectral slopes and infrared brightness profiles of these very high redshift sources seem to fit a model that fits this idea. The impossible mass problem. Astronomers thought that the first high redshift galaxies found by the James Webb Space Telescope would be small, consisting only of groups of a few million stars starting to come together. Instead, Webb found things that were as massive as or even more massive than the Milky Way, and they existed only a few 100 million years after the Big Bang theory says time began. Researchers were shocked by the finding because every computer model of how the universe evolved said that the growth should not have been possible. Being billions of solar masses so soon after the Big Bang shouldn't have been possible because galaxies shouldn't have had enough time, matter, or gravity. The most discussed example came from the Cosmic Evolution Early Release Science (CEERS) survey. Webb identified several galaxies between redshift 10 and 13 with stellar masses approaching 10 billion solar masses. That's roughly the same mass as the Large Magellanic Cloud, a satellite galaxy that, in our timeline, took 13 billion years to form. The puzzle was immediate. How could the universe assemble so much material in barely 1% of its lifetime? The rate of star formation required to build those systems would need to be hundreds of times faster than anything observed later in cosmic history. In cosmology, growth depends on the slow accumulation of gas within dark matter halos. These halos, gravitational wells made of unseen matter, act as scaffolding for ordinary baryonic gas to cool, condense, and ignite into stars. Simulations such as Illustris-TNG and FIRE predict how that process unfolds over billions of years. Yet when Webb's data is plugged into these models, the results break down. The halos needed to host these early giants simply shouldn't exist at that epoch. There hasn't been enough time for density fluctuations in the cosmic web to grow into the massive structures required. To test whether the data might be misleading, astronomers examined the possibility of lensing, foreground galaxies magnifying the light of distant dwarfs, but Webb's sharp resolution and multi-angle imaging ruled that out for most candidates. The luminosity, spectra, and surface brightness profiles all indicated genuinely large, mature systems, not optical tricks. Even if lensing contributed, the magnification factors needed to make small galaxies look this bright would require enormous lensing clusters directly aligned along the line of sight, and none were found. The next step was to question star formation efficiency. Maybe early conditions allowed gas to form stars far more rapidly than expected. But star formation is limited by feedback. Radiation, winds, and supernova from newborn stars blow gas away before it can collapse further. Pushing efficiency beyond 20% breaks the physics of feedback itself. To reach the masses, Webb observes, early galaxies would need efficiencies of 100% or more, every available atom converted into stars almost instantly. That's not just extreme, it's physically inconsistent. So scientists started to look into ideas that were not the norm. One idea is the primordial black hole seed theory, which says that if huge black holes existed before regular matter did, their gravity could have sped up the flow of gas into galaxies, rather than the other way around. Non-standard dark matter is another idea. It might clump together more tightly than cold dark matter suggests, making deeper wells for baryonic matter to fall into. Some even say that early episodes of dark energy loss briefly made some areas heavier. Each theory tries to stretch the timescale of the universe just a bit to explain these masses, but none of them yet give a clear answer that can be tested. If the data stands, it may mean our picture of the early universe is fundamentally incomplete. Perhaps the Big Bang wasn't a smooth, uniform beginning, but a transition layered with relic structures, cosmic debris from a previous era that gave matter a head start. In that case, some of the massive galaxies Webb sees could be rebuilt, gravitationally reassembled from pre-existing material rather than born from scratch. It's a controversial idea, but one that gains traction as more anomalous galaxies appear in Webb's catalogue. Light from a hidden epoch. Before James Webb, every telescope had a blind spot, or a wall of darkness. That wall was the cosmic microwave background, which is the glow left over from the Big Bang. It marks the moment, about 380,000 years after the universe began, when light could first move easily through space. Before that, the universe was a cloud of charged particles that sent photons flying in all directions. As far back as we could see, astronomers called it the surface of last scattering. We thought that was all. When Webb began its deep field surveys, researchers expected to approach that barrier but never cross it. Yet something strange appeared in the faintest corners of its infrared data, an unexplained glow. Spread thinly across multiple deep fields, this light didn't match any catalogued galaxies, stars, or even known diffuse background sources. It wasn't zodiacal light from dust in our solar system, nor was it instrument noise. It was coming from somewhere far older than any structure we could explain. To understand how radical that is, remember that the cosmic microwave background, CMB, represents the earliest light we should ever detect. Its radiation has cooled over billions of years to a gentle 3 degrees above absolute zero, glowing faintly in microwave wavelengths. But Webb doesn't observe microwaves. It sees infrared. That means the strange light it's detecting isn't the CMB itself, but something behind or beneath it, stretching further back in time than the standard model allows. NASA scientists call this extragalactic background light, or EBL, the cumulative glow of every source that has ever existed, including ones too faint or too distant to resolve. But Webb's measurements show that the EBL is brighter than all known galaxies combined. Something else is contributing to it. When researchers subtracted every accounted source, every star, every nebula, every faint dwarf, they were left with a residual infrared signal that shouldn't be there. Some describe it as ghost light, a leftover luminescence from a hidden epoch of the universe. The most straightforward explanation is that Webb is seeing clusters of tiny, ancient stars that haven't yet been individually resolved. But their brightness profile doesn't fit that theory. The distribution is too uniform, too smooth across the sky. Others suspect that the light could come from disintegrating dark matter, hypothetical particles releasing low-energy photons over cosmic time. That idea, though, faces its own challenges. Dark matter has never been directly observed, and the specific decay mechanisms needed to produce this glow remain speculative. There is a more bold theory that points to something even deeper. Some cosmologists think that this background is a remnant radiation field from before the Big Bang. They see it as a faint echo from a universe that existed before ours, that left its energy mark on ours. In circular or bounce cosmologies, the universe shrinks, gets hotter, and then starts to grow again. If that were true, some of its photons might have been able to make it through the change, shifting into infrared bands over a huge amount of time. Webb could be the first instrument to pick up their signals because it is so sensitive. To test the signal, scientists compared Webb's data with measurements from earlier missions like Spitzer and COBE. Spitzer had also detected an unexplained infrared excess, but couldn't resolve its pattern. Webb, however, has confirmed its structure with far greater clarity. The background light appears isotropic, uniform in all directions, suggesting a cosmological origin rather than a local one. That uniformity is eerily similar to the CMB itself, except hotter and older by nature. Some theories, like Dr. Rogier Windhorst from Arizona State University, have said that this finding is like seeing the faint heartbeat of the universe. Some people are more skeptical, saying that the glow could still be caused by cosmic dust spreading starlight. Astronomers are now comparing Webb's readings with information from Euclid, an ESA project, and the Nancy Grace Roman Space Telescope, which is about to be launched. If all three find the same extra, it's a huge sign that there really was a secret era. The ghost stars hypothesis. Astronomers noticed something very strange when the James Webb Space Telescope started to resolve its first group of galaxies with high redshift. Some of these galaxies didn't look young in terms of their spectra. Their light had chemical fingerprints of carbon, oxygen, and even iron, which meant that many generations of life and death in stars had already happened. But the timeline for the Big Bang showed that there hadn't been enough time for even one full generation of stars to form, burn out, and add heavier elements to the universe. These strange spectrum fingerprints made us wonder if some of Webb's stars were older than the universe itself. To understand why this is so significant, consider what astronomers expected. The very first stars, known as population 3 stars, were supposed to be made entirely of hydrogen and helium, the pure ingredients forged in the Big Bang. They were thought to form roughly 200 million years after time began, live violently and die quickly, producing the first heavy elements that enriched later generations of stars. But Webb's infrared data show metal lines, signs of elements heavier than helium, appearing far too early. That means those stars weren't truly first generation at all. They were already second or third generation systems, implying something before them must have existed. People have called these strange stars ghost stars. This phrase doesn't mean ghosts, but rather groups of stars that seem to hold the memory or even the matter of a past cosmic age. Their light points to pre-enrichment, which means that metals were already present in the universe before the Big Bang. Every chemistry evolution model we have now is thrown into chaos by that idea. When Webb's NIRSPEC instrument analyzed the spectrum of a galaxy designated Jade's GS-Z 13-0, astronomers found features consistent with mature stellar populations, stars that had already gone through internal fusion cycles beyond hydrogen. The Balmer breaks in their spectra, a telltale sign of older, cooler stars, were too pronounced to belong to a universe still in its infancy. If these measurements hold, it would mean stars had been forming when the universe was only 250 million years old, or perhaps even earlier, during a phase that current physics doesn't describe. One explanation gaining traction is that these stars may be the descendants of matter surviving from a previous cosmic cycle. In cyclic or bounce cosmologies, each universe expands, contracts, and gives rise to another, with traces of old matter carried forward. These traces, collapsed remnants, compact objects, or black hole seeds, could have acted as gravitational anchors, accelerating star formation in the new epoch. In that case, Webb's ghost stars are not truly older than the Big Bang, but inherit their composition from a universe that came before it. It's also possible that time moved differently in the early stages of the world. According to quantum cosmologists, time may have sped up when there was a lot of matter in the universe. This could have made processes like star evolution happen faster than they would now. It's just a guess, but it could help fit many generations of stars into the small time frame between the Big Bang and Webb's findings. Skeptics, however, argue that the apparent maturity of these stars may stem from misinterpretation. Perhaps energetic radiation or gravitational lensing distorts their spectra, mimicking metal lines or older populations. Yet even with those corrections, the observed abundance of heavier elements remains uncomfortably high. In multiple datasets, jades, sears, and glass, the same pattern appears. Too many metals, too soon. Cosmic dawn rewritten. Astronomers have had a clear idea of what the cosmic dawn should look like for many years. The first 100 million years, when hydrogen clouds spread out and came together under gravity to form the first stars, was supposed to be a crazy, confusing time. They thought these early buildings were small, crooked, and insecure. They burned quickly, burst furiously, and threw a lot of debris into space, making room for galaxies that would form later. But the James Webb Space Telescope didn't see chaos when it looked back to that time. It found order in galaxies that were bright, close together, and already well structured. It was like the universe had skipped the awkward teen years and gone straight to being an adult. Webb's deep field images from the Jades and Sears surveys showed galaxies forming just 300 and 400 million years after the Big Bang. Yet, even at that early stage, many displayed clear disc-like shapes and even the faint suggestion of spiral arms. That finding defied everything cosmologists thought they knew about galactic evolution. In existing simulations, it should have taken billions of years for galaxies to settle into such ordered motion. Instead, Webb revealed rotation, gravitational balance, and composure in a universe that was barely a few 100 million years old. It didn't just change one part of astronomy, it ruined several of them. Scientists thought for a long time that galaxies started out as rough clouds that kept merging, growing through crashes and chaos. The rough model fit well with what Hubble saw, which were light spots that were weak and fuzzy. But Webb's infrared sensitivity was better than Hubble's, so it could see more detail. Galaxy shapes were not empty in that deeper layer after all. It was already hard for them. That made scientists think again about whether gravity and dark matter behaved differently in the early universe, or whether the stuff that stars are made of was affected by something older, like an environment that was there before the Big Bang. Some theorists suggest that baryonic matter, the normal atoms that make up stars, might have condensed more quickly in certain regions because of unusually dense concentrations of dark matter. Others point to the possibility of cosmic preceding, where material from an earlier universe compressed into our own expansion, giving galaxies a head start. Even more conservative scientists are uneasy with how perfectly ordered Webb's early galaxies appear. The presence of rotational symmetry and heavy elements in systems so close to the beginning of time seems to demand new physics, or at least a major correction to the LCDM, lambda cold dark matter model, that dominates cosmology. A really fascinating thing that Webb found was through the GLASS program, Grism Lens Amplified Survey from Space. It found galaxies like GLASS Z12, which was formed only 350 million years after the Big Bang, but looked like they had billions of stars because they were so bright and well organized. For these kinds of systems to form so quickly, the universe would have had to either cool down hydrogen gas more quickly or go through a time of early strong gravitational collapse, which are both things that current models don't take into account. These findings suggest the cosmic dawn may have started far earlier than previously thought, possibly within just 100 million years of the Big Bang. That would push back the timeline of reionization, the process that made the universe transparent to light, by several 100 million years. It also means the so-called Dark Ages, the period between the Big Bang and the first light, may not have been so dark after all. There could have been small bursts of illumination, the first glimmers of complex structure, long before our models ever predicted them. Dark stars or dark energy? Among the weirdest ideas that has come out of the James Webb Space Telescope's work is that the biggest things it sees from the beginning of the universe might not even be galaxies or stars. They could instead be dark stars, which are huge things that get their power not from nuclear fusion, but from the destruction of dark matter. It sounds like something out of science fiction, but Webb's data has given it new life, making cosmologists wonder if the universe's first light didn't come from normal matter, but from the mostly unseen stuff that makes up the universe. For decades, dark matter has been treated as a quiet background actor. It doesn't emit light, doesn't absorb radiation, and interacts with visible matter only through gravity. Yet it accounts for roughly 85% of the universe's total matter content. According to conventional models, dark matter's main role is structural. It provides the gravitational scaffolding that pulls ordinary gas together to form galaxies. But what if, in the universe's infancy, dark matter did something more dramatic? What if it glowed? That's the premise behind the dark star hypothesis, first proposed in the mid-2000s. Physicists like Catherine Fries and Paolo Gondolo suggested that in the earliest, densest regions of space, clouds of dark matter particles, specifically weakly interacting massive particles, or WIMPs, could collide and annihilate, releasing energy in the process. That energy could heat surrounding gas and prevent it from collapsing too fast, creating enormous, long-lived stars powered not by fusion but by dark matter annihilation. These dark stars could reach sizes hundreds of times larger than the Sun and shine for millions of years without ever burning normal fuel. When the James Webb Space Telescope began detecting impossibly bright compact sources at redshifts greater than 10, the dark star theory suddenly gained traction again. Some of Webb's early observations, like those in the JADES and Sierras surveys, revealed luminous points of light that didn't behave like typical young galaxies. Their brightness profiles were too intense and their colors too uniform, lacking the variation expected from star clusters or nebula gas. In particular, several objects, such as Sierras 1019, appeared to emit light with temperatures and spectra that match predictions for dark stars rather than for ordinary stellar populations. If even one of these candidates turns out to be a true dark star, the implications would be immense. It would mean that dark matter isn't entirely inert. It can release energy under certain conditions, influencing the early universe in direct, luminous ways. That could help explain how the first massive structures formed so quickly after the Big Bang. The additional heating and pressure from dark star radiation could delay or alter the normal process of star formation, creating environments where galaxies assemble differently than models predict. Critics argue that the spectral signatures Webb sees could just as easily be explained by compact, active galactic nuclei, small black holes at the centers of early galaxies that are consuming gas at extreme rates. Others point to the possibility of superstar clusters, densely packed regions of young stars that can mimic the brightness of a single massive object. Webb's instruments can't yet distinguish between these scenarios with absolute certainty, but follow-up spectroscopy will help narrow the options. If dark stars did exist, they would eventually die in spectacular fashion. Once their dark matter fuel ran out, they would collapse under their own gravity, possibly forming massive black holes far earlier than ordinary stellar evolution would allow. Those early black holes could explain another of Webb's puzzles: the presence of supermassive black holes less than 1 billion years after the Big Bang. In that sense, dark stars could be both the first lights of the cosmos and the seeds of its darkest objects. Pre-bang echoes in the background. The cosmic microwave background, which is the faint glow left over from the Big Bang, has been the universe's oldest piece of proof for almost 60 years. This is the light that was given off when the universe was only 380,000 years old. It covers the sky in a pattern of temperature and density that is almost perfect. But when the James Webb Space Telescope started to gather deep infrared data, cosmologists began to notice small differences between the old readings that they had been using and the new ones. Webb's sensors picked up on faint organized light that didn't fit with the timing of the Big Bang. Under the chatter, there seemed to be an older sound. This anomaly first came to attention when researchers compared Webb's ultra-deep fields to the precise microwave maps made by ESA's Planck satellite. The Planck mission had already catalogued slight cold and hot spots, tiny fluctuations that represent the seeds of future galaxies. But Webb's data, sensitive to different wavelengths, showed patterns that didn't correspond to any known structure in those regions. Even after subtracting light from visible galaxies, interstellar dust, and instrument noise, a whisper of organized brightness remained. Some cosmologists began calling it the infrared echo, a possible signal from before the Big Bang's observable horizon. One theory points to gravitational wave fossils, ripples in space-time produced by violent events predating the hot Big Bang. These waves could have slightly altered the density of space, leaving behind regions where light curves or stretches in unusual ways. Webb, with its precision infrared imaging, might be sensitive enough to pick up those distortions as irregular background patches. If that interpretation holds, it would mean the telescope isn't just looking back in time, it's detecting the gravitational fingerprints of a universe that existed before ours expanded. Other scientists focus on strange circular patterns that have appeared in both Planck and Webb datasets. Cosmologist Roger Penrose, through his conformal cyclic cosmology model, proposed that these circles in the sky could be remnants of black holes evaporating at the end of a previous cosmic cycle. As those ancient holes released their final radiation, they could have imprinted concentric scars onto space-time itself, scars that might now appear as faint uniform rings in background data. Webb's higher resolution offers a way to test that idea. By mapping whether these patterns correlate across multiple deep fields, astronomers can determine whether they're random noise or the marks of an older universe burned into the fabric of ours. Some teams argue that intergalactic dust could scatter background light, producing subtle gradients that mimic pre-bang signatures. Others suggest that foreground galaxies at intermediate distances may be blending together in ways that fool even Webb's sharp eyes. The challenge is that these differences are faint, fractions of a percent above the expected brightness, and verifying them demands multiple instruments. That's why missions like Euclid and the Nancy Grace Roman Space Telescope will be crucial. They'll cross-check Webb's deep infrared data with optical and near-infrared observations to see if the same echoes persist. If the signal does stand up to scrutiny, though, the results are shocking. It would mean that the universe has a memory, a record of how things were before we knew what space and time are. Instead of a single beginning, the Big Bang may have been a change, a rebound from an earlier shrinkage of the universe. The extra light Webb sees might be the last rays of that earlier universe, stretched by unimaginable growth into the faint background we see now. The phantom redshift illusion. How can you be sure that what you see is real? This is a question that all big telescopes have to answer. This is also true for the James Webb Space Telescope. Its most shocking finds, galaxies that look like they are older than the Big Bang, depend on just one measurement: redshift. The whole claim falls apart if that number is even slightly wrong. As a result, more and more scientists are asking a difficult question. What if Webb isn't seeing old galaxies at all, but something much closer? Something that's making our tools think it's from before time. Redshift is supposed to be simple. The farther away an object is, the faster the universe's expansion stretches its light, making it redder. Webb detects this by splitting light into its spectrum and measuring how much the known emission lines of hydrogen, oxygen, and carbon have shifted toward longer wavelengths. But there's a catch. Many different cosmic processes can mimic that same stretching. Gravitational lensing is one potential cause. This is when light from galaxies farther away is bent and enlarged by large galaxies in the region. The change in size can change the color and light of a galaxy, making it look older and farther away. In some of Webb's deep field pictures, tiny lines of light might be lensed pictures of normal local galaxies that have been stretched to look bigger than they really are. But when scientists looked for lensing clusters in those areas, they often couldn't find any that were strong enough to explain the very high redshifts that were being recorded. Dust disturbance is another reason. Cosmic dust grains can take in blue light and send out infrared radiation again, making them look like very far away things. In a way, dust can make a galaxy that isn't too far away look redder. Because Webb has unmatched infrared sensitivity, it is especially sensitive to this effect because it can see weak dust glows that older telescopes just missed. But if you carefully measure the spectral lines, you can tell if the red color is caused by motion or absorption. So far, most of Webb's potential galaxies have straight, clean lines, which means that dust is probably not the whole story. There's also the issue of line misidentification. Sometimes, faint emission lines can overlap or mimic each other. A galaxy at moderate distance might have its oxygen line mistaken for the hydrogen line of a far more distant object. When that happens, the computed redshift skyrockets. Early in Webb's mission, several record-breaking galaxies were later reclassified after deeper spectroscopy corrected such errors. Even so, many candidates, like JADE's GSZ 14-0, have survived repeated verification with multiple instruments. This debate touches the heart of scientific caution. Webb's discoveries are extraordinary, and extraordinary claims demand extraordinary confirmation. That's why multiple teams are cross-checking each high redshift galaxy using independent data and comparing brightness curves with models of known stellar populations. Every successful confirmation strengthens the case that these galaxies really do belong to an age when the universe was just a few 100 million years old. Every correction, meanwhile, reminds scientists how easy it is for even precision instruments to be deceived by cosmic complexity. Yet even among skeptics, the illusion argument raises deeper philosophical unease. If our instruments can be fooled into seeing pre-Big Bang galaxies, what else might be masquerading as ancient light? Could overlapping gravitational fields or unknown quantum effects in the early universe stretch light in ways we don't yet understand? Some theorists have begun exploring models where extreme cosmic curvature could create false redshift zones, pockets of warped spacetime that bend photons to appear far older than they are. The JADES anomalies. The JADES survey, which stands for the JDWS Advanced Deep Extragalactic Survey, was meant to prove what cosmologists already knew. It was meant to be one of Webb's most important projects. It was a deep look into two well-studied areas of sky called the Goods fields, where Hubble had already found the smallest galaxies. JADES would go even further by putting together Webb's near-infrared camera, NIRCam, and near-infrared spectrograph, NIRSpec, to make the most accurate record of how galaxies formed in the early universe ever seen. The simple hope was that it would fill in the gaps between known epochs and show how order slowly grew out of chaos. In late 2022, just months after Webb's first images were released, the JADES team identified a galaxy named JADES GSZ13-0. Its light was so redshifted that it appeared to come from just 325 million years after the Big Bang, making it the oldest galaxy ever observed at the time. Even more baffling, it was bright, too bright. Its mass and luminosity suggested hundreds of millions of stars, a level of complexity the universe shouldn't have reached for another 400 million years. And then came the second shock. JADES GSZ14-0, another galaxy, even farther, whose light dates to roughly 290 million years post-Big Bang. Two record breakers, one after another, in the same field. To scientists used to the slow, predictable rhythm of cosmic history, this was like discovering skyscrapers in a Stone Age village. According to the LCDM model, galaxies at those times should have been no larger than a few 100 million solar masses. But the JADES objects appeared 10 to 100 times heavier. It wasn't just their size. Their light carried chemical signatures of stars that had already gone through life cycles. These galaxies weren't infant structures. They were adolescents in a universe that had barely learned to walk. The shockwaves through cosmology were immediate. The LCDM model, which combines cold dark matter with a cosmological constant to describe expansion, had withstood every major observational challenge for 2 decades. Now it faced data that it simply couldn't explain. Simulations that previously reproduced large-scale cosmic structure failed to generate anything close to these galaxies at that age, no matter how scientists tuned the parameters. The math broke down. Critics initially pushed back. Maybe JADES had mistaken red color for redshift. Perhaps dust or overlapping sources fooled the instruments. But Webb's NIRSpec spectrograph settled the issue by capturing the precise spectral break caused by hydrogen absorption, the unmistakable marker of high redshift. These galaxies were real. They were ancient, and they were impossible. What else could explain them? It's possible that the universe made stars much faster and better than models show. Standard theory says that young stars and supernovae can slow down the rate at which gas can turn into new stars. But if the early dark matter halos were thicker than thought, they might have caught more gas, which would have sped up growth. On the other hand, primordial black holes, relics from the very beginning of the universe, might have served as gravity anchors, pushing matter together faster than normal physics allows. Webb's views of some JADES galaxies' centers being very small and bright back up this idea. A more radical explanation is that these galaxies aren't first-generation structures at all. Some cosmologists argue they could be recycled systems, remnants of matter that survived a previous cosmic cycle and reassembled after the Big Bang. This would fit the peculiar chemical signatures Webb detected. Traces of heavier elements like carbon and oxygen, where none should yet exist. In other words, the Jade's galaxies might not be young universes forming, but old ones reborn. What's more surprising is how well planned these systems look. Images from Jades show signs of spin, symmetry, and geometry, which is not what you would expect from the early universe, which is chaos. If it's true, it means that the early universe's conditions were more stable than thought. That steadiness could mean that inflation was weaker, or that the universe cooled more slowly after the Big Bang, which are both possibilities that are different from almost every textbook model. The scientific community responded with a mix of awe and caution. Some hailed the results as evidence that cosmology was entering a new era of revision. Others, like Nobel laureate John Mather, urged restraint. We've been wrong before about firsts. Let's see if these stay the oldest. But the Jade's anomalies didn't fade with more data. They multiplied. As Webb's deep field surveys expanded, astronomers kept finding more galaxies in the same time window, all sharing the same impossible characteristics: high mass, high brightness, and mature chemistry. By 2024, more than a dozen candidate galaxies had been logged at redshifts greater than 13. The odds of all of them being misidentified are vanishingly small. Instead, the weight of evidence now suggests that the early universe was far busier and brighter than anyone predicted. This realization has triggered a flurry of theoretical work. Some propose modifying the nature of dark matter itself, replacing it with warm or self-interacting dark matter that clumps faster. Others advocate for new cosmological models entirely: early dark energy, variable speed inflation, or cyclic bounce scenarios where remnants from older universes jumpstart structure in newer ones. Hydrogen that shouldn't be ionized. The James Webb Space Telescope found something very strange that wasn't a bright galaxy or a mysterious dark star. It was hydrogen, which is the most common element in the universe. Astronomers thought they knew the story of it exactly for many years. It was a cold, neutral gas that filled the world after the Big Bang. After hundreds of millions of years, when the first stars were born, their ultraviolet light started to reionize the gas. This took electrons away from hydrogen atoms and made the world clear for light. It was thought that this big change, called the Epoch of Reionization, would happen between 400 million and 1 billion years after the Big Bang. But Webb's deep field spectroscopy has found something that shouldn't exist in that era: ionized hydrogen appearing much earlier than it should. The telescope's instruments, designed to detect the faintest emission lines in the infrared, have captured signatures of ionized hydrogen, particularly the strong Lyman alpha and H alpha lines, in galaxies that existed only 250 million years after the Big Bang. That's far too soon. By all conventional estimates, the universe should still have been blanketed by neutral hydrogen, making it opaque to such light. Yet Webb's spectra show otherwise: bright, unmistakable traces of a reionized universe already in progress. To understand how disruptive that finding is, it helps to recall what the cosmic timeline predicted. Between the Big Bang and the first stars lies a period called the Dark Ages, when light could not freely travel because neutral hydrogen absorbed and scattered it. When the first stars began fusing hydrogen into heavier elements, their radiation slowly ionized surrounding gas, carving out expanding bubbles of transparency. Those bubbles eventually overlapped, allowing starlight to move freely through space, the moment the universe became visible. But Webb's observations suggest those bubbles formed far earlier and grew much faster than standard models predict. In the Jades and Sears surveys, astronomers found strong spectral emission from ionized hydrogen in galaxies at redshifts greater than 12. That corresponds to just 350 million years after the Big Bang, roughly twice as early as expected. Even more puzzling, some of those galaxies appear embedded in regions that should still be dominated by neutral hydrogen. In theory, their light should have been completely absorbed long before reaching us. The simplest conclusion is that reionization began earlier, but the implications are enormous. It means the universe's first stars and galaxies were forming and shining long before our cosmological models allow. Researchers have proposed several explanations. One is that population 3 stars, the universe's first massive metal-free stars, might have been far more numerous and energetic than we thought. If these giants burned hotter, they could have emitted intense ultraviolet radiation capable of ionizing hydrogen over vast distances. But Webb has yet to identify unambiguous population 3 candidates. Instead, the galaxies it sees already contain metals, suggesting even these early systems had previous generations of stars. An impossible paradox if the universe was just beginning. A further hypothesis is that quasars or early black holes were the main cause of reionization. If big black holes were already absorbing gas at this time, their X-rays could have charged hydrogen much more effectively than light from stars alone. The fact that Webb found active galactic centers in some early galaxies that were surprisingly bright adds support to that idea. There were, however, such huge black holes around at that time, which brings up another question. How did they form so quickly? Some cosmologists have gone further, suggesting that what Webb is observing might not belong entirely to our own cosmic era. The light could be leaking in from a pre-Big Bang phase, remnants of radiation left over from a previous cycle of the universe. In that case, the apparent ionization might be a fossil signature, photons that survived the last contraction and re-expansion of space-time. Though speculative, this theory would explain why the observed ionization doesn't match any known energy source within the early universe itself. The ultramassive black holes problem. One puzzle that ties together almost all of the surprises from the James Webb Space Telescope is how giant black holes could have been around in the beginning of the universe. Astronomers thought for a long time that stars millions to billions of times heavier than our Sun took billions of years to form. Over the course of cosmic time, they slowly formed as gas clouds collapsed and galaxies joined together. Deep field studies by Webb have found a strange contradiction. Black holes with huge masses already existed less than 500 million years after the Big Bang. That is, the universe hadn't even formed stable galaxies yet, but there were already monsters living in the centers of them. One of the earliest examples came from a galaxy now famous among cosmologists, Sears 1019, observed by Webb in mid-2023. The telescope detected an active galactic nucleus, a bright core powered by material spiraling into a central black hole, in a galaxy that existed just 570 million years after the Big Bang. By measuring its luminosity and emission lines, scientists estimated the black hole's mass at roughly 10 million solar masses. That might sound modest compared to the billion solar mass engines in modern quasars, but its presence at that time is nearly impossible under standard physics. To reach that size so quickly, it would have needed to start as an enormous seed, accreting matter at a rate far faster than theory allows. And Sears 1019 was not unique. Webb's NIRSPEC and MIRI instruments have since identified several similar cases, compact, hyperluminous cores at redshifts above 10. Each displays emission patterns consistent with accreting black holes. The implication is unmistakable. Black holes were not rare in the early universe. They were common. The only question is how they got so big, so soon. In the Standard Model, a black hole begins as the remnant of a massive star, perhaps 100 times the mass of the Sun, which collapses after exhausting its fuel. From there, it can grow only by pulling in surrounding gas or merging with other black holes. But that process is painfully slow. Radiation pressure from infalling gas limits how fast the material can accumulate. This limit is known as the Eddington rate. Even if a black hole accreted at that rate non-stop since the Big Bang, it couldn't have reached 10 million solar masses by 500 million years. Something else must have happened. The direct collapse model says that huge clouds of hydrogen and helium from the beginning of time could fall straight into black holes without first making stars. This type of black hole could begin with a mass tens of thousands or even hundreds of thousands of times that of the Sun. This gives it an advantage, but they can only form in very specific places, areas with strong ultraviolet light that stops stars from forming and lets gas fall apart easily. That doesn't seem likely to happen everywhere Webb sees black holes, which would explain why there are so many of them. A different theory is that the seeds came from a time even further back, maybe even before the Big Bang. In some models of the universe, especially circular or bounce universes, black holes can live through the end of one universe and start a new one. Before there were stars and galaxies, there were these old things called primordial black holes. They might have been gravitational seeds that drew in matter to make the first galaxies around them. Webb's early pictures seem to back this idea. Then Webb isn't just seeing young black holes that are growing quickly, he's seeing old black holes that are still around from a universe that was here before ours. Some theorists propose that during the earliest fractions of a second after the Big Bang, density fluctuations in the primordial plasma could have produced black holes directly, without stars or galaxies involved. If regions of space were even slightly denser than average, their gravity could have caused immediate collapse. The resulting black holes, ranging from microscopic to massive, might have persisted through cosmic expansion, merging into the behemoths Webb now detects. Webb's instruments have already captured tantalizing clues supporting these possibilities. In several early galaxies, the light from their cores shows chemical signatures, high ionization lines of nitrogen and oxygen, that indicate intense radiation consistent with accreting black holes. These galaxies also appear unusually compact, suggesting that black holes dominated their formation, shaping their growth from the inside out. In one case, the black hole seems to make up nearly 10% of its host galaxy's total mass, a ratio unheard of in the modern universe. If such proportions were common, it means the relationship between black holes and galaxies, long thought to be one of gradual coevolution, was completely different in the beginning. Instead of galaxies forming first and nurturing black holes at their centers, the reverse may have been true. Black holes came first, gathering matter to build galaxies around them. It's an inversion of cosmic hierarchy, one that turns the Big Bang's timeline inside out. This option is directly linked to the bigger question of whether the Big Bang was a single start or a change. If primordial black holes really are older than the universe, then Webb isn't just seeing the first generation of cosmic structures, it's seeing the last of what was there before. Each one is like a heartbeat that has been preserved from a different time. They hold the mass and memory of a universe that ended and began again. Primordial heavy elements. The Big Bang model has always been based on a simple idea that when the universe was first formed, it only made hydrogen, helium, and a small amount of lithium. Iron and gold, as well as carbon and oxygen, had to be made in the hearts of stars later on. Because of this, scientists were shocked when the James Webb Space Telescope found heavy elements, or metals, in galaxies that were formed only a few 100 million years after the Big Bang. It really shouldn't have been possible. It was thought that the universe would still be clean and free of the fusion cycles that make things complicated. But Webb's infrared spectrum shows that chemicals were fully developed long before stars had time to do so. The discovery came gradually. Webb's NARSpec instrument, capable of splitting faint light into its elemental fingerprints, recorded emission lines of oxygen, carbon, neon, and even iron in galaxies at redshifts above 10. One example, a compact galaxy observed during the JADE survey, displayed oxygen and silicon lines so strong that astronomers initially thought the data were corrupted. But multiple independent observations confirmed it. Those elements were really there, shining in a universe that should have known only hydrogen and helium. The implication was staggering. It meant that several generations of star birth and death had already occurred within just 300 million years of the supposed beginning of time. The traditional chemical timeline couldn't accommodate that. Heavy elements form when stars fuse lighter atoms in their cores and then explode as supernovae, scattering those elements into space. Each cycle takes hundreds of millions of years. To see significant metallicity that early means those cycles had to be compressed. Either stars were forming and dying much faster than expected, or the universe inherited its metals from somewhere else. The first idea, accelerated star formation, struggles with physics. Massive stars do burn quickly, but even they can't recycle enough material in such a short span to explain the abundances Webb detects. The second idea is far more radical: pre-enrichment. It proposes that the early universe wasn't chemically pristine at all. Instead, it was born already seeded with heavy elements, relics from a previous cosmic epoch. Support for this idea comes from the ratios of metals that Webb observes. In many early galaxies, oxygen to carbon and silicon to iron ratios differ sharply from what's expected if they were produced by standard stellar nucleosynthesis. The patterns suggest these elements weren't formed in normal stars, but in an earlier exotic environment, possibly the final stages of a previous universe collapsing into the Big Bang. When that prior cosmos contracted, its matter may have reached densities high enough to trigger fusion on a universal scale, generating metals before being blown apart into the next expansion. Those heavy nuclei could have survived the transition, carried across the bounce as microscopic dust or bound particles, waiting to be incorporated into new stars. This notion aligns with the cyclic cosmology idea proposed by theorists such as Roger Penrose and Paul Steinhardt, the view that universes don't begin or end, but pass through endless sequences of contraction and rebirth. In such a model, entropy resets during each bounce, but matter, or at least some of its building blocks, can persist. If Webb's metal-rich early galaxies are genuine, they could represent the first observational evidence that the Big Bang wasn't a one-time event, but part of an eternal cycle of cosmic recycling. Even within a single universe framework, these early metals are difficult to explain. Some researchers argue that massive population 3 stars may have lived and died much faster than simulations predict, producing supernovae powerful enough to scatter metals across vast regions of space almost instantly. Others suggest that direct collapse black holes could have created jets and radiation strong enough to trigger premature nucleosynthesis in surrounding gas clouds. Yet neither model fully explains the uniformity of metal enrichment Webb observes. The distribution is too widespread, too consistent, as though the universe began already stirred. The warmth of early galaxies is another interesting hint. Webb's mid-infrared scans show that some systems give off dust radiation patterns that are common in mature settings with a wide range of chemicals. That dust must have carbon grains and silicates in it, which are substances that can only be made after stars have died many times. Astronomers even found signs of polycyclic aromatic hydrocarbons in one galaxy. These are complicated molecules with many carbon rings. Finding them so soon after the Big Bang is like finding skeletons on mud that has just cooled down. They are proof of a past that shouldn't exist. The first chemical cycle. Astronomers understood they weren't just studying stars when the James Webb Space Telescope started to map the chemical signatures of the oldest galaxies. They were seeing chemistry come to life. That story was told in every line in Webb's spectrum: hydrogen giving way to helium, helium giving way to carbon, and carbon giving way to oxygen, silicon, and iron. Researchers were shocked not only by how quickly this process happened, but also by the idea that it had happened before. To understand why, it helps to revisit how chemical evolution is supposed to work. After the Big Bang, the universe was almost entirely hydrogen and helium. The first stars, massive, short-lived, and pristine, fused those light elements into heavier ones in their cores. When those stars died in supernovae, they expelled their ashes into surrounding space, enriching the next generation of stars with metals and dust. Over billions of years, this cycle repeated, creating the chemical diversity we see today, from the oxygen we breathe to the calcium in our bones. But Webb's discoveries suggest that the first chemical cycle occurred far too early, and on a scale too vast to fit that neat sequence. The telescope's NIRSpec and MIRI instruments detected high metallicity, abundant heavy elements, in galaxies that existed just 300 million years after the Big Bang. To produce that much enrichment, at least 2 complete stellar generations must have lived and died before Webb captured their light. Yet cosmic time doesn't allow it. Even if the first stars formed immediately after the universe became transparent, their lifespans and explosion timescales simply can't add up. The numbers imply an impossible head start, as if chemical evolution began in an era that predates our known universe. Some astrophysicists propose a pre-Big Bang enrichment phase, an echo of a prior cosmic cycle whose dying stars seeded our own universe's birth cloud. In this model, matter from an earlier universe was compressed during a bounce or transition event, mixing its already processed material with the primordial plasma that followed. When the new universe expanded, it wasn't chemically blank. It carried the ashes of its predecessor. These relic atoms would explain why even the earliest galaxies appear too mature, their spectra already bearing the fingerprints of multiple element-forming generations. But there is a more realistic possibility. The first stars may have been even bigger and more powerful than we thought. Webb's findings hint at pair instability supernovae, which are supermassive explosions that happen in stars with more than 140 times the mass of the Sun. These kinds of events release huge amounts of heavy elements all at once, making the environment better almost right away. There is a chance that the first chemical cycle could have been completed in tens of millions of years instead of hundreds of millions. Even so, that situation doesn't fully explain why metals are spread out evenly in worlds far away. Too many of the chemical fingerprints are the same, which points to a bigger, older source. One clue lies in Webb's detection of dust grains, carbon-rich compounds, silicates, and iron crystals, in places that predate the known timeline for dust formation. Dust requires not just metals, but stable environments where molecules can form and survive. Yet Webb found these grains in galaxies less than 400 million years old. Their presence indicates that star death and element recycling were already in full swing, implying that the universe's first chemical loop had completed itself in record time. If that's the case, then the first chemical cycle wasn't truly first at all. It may have been a continuation, a cosmic inheritance. Each star, each atom, could be a recycled part of an older reality, rewritten and reassembled under new physics. This idea transforms the Big Bang from an absolute beginning into a phase transition, much like water boiling into steam, a change of state, not of existence itself. The cycle of matter, fusion, and explosion would then be eternal, stretching across universes. Even within standard cosmology, Webb's discoveries rewrite textbooks. The rate of chemical evolution must be increased dramatically. The birth of the first heavy elements pushed closer to the universe's origin. Astronomers now model rapid metal production using hypernova feedback. The idea that early massive stars exploded so violently they spread elements at nearly the speed of light. This would allow metals to disperse across cosmic distances in a fraction of the expected time. But it still doesn't explain why so many early galaxies share the same baseline metallicity, as if they all started from the same enriched source. Ghost light between galaxies. Astronomers thought the deep dark spaces between galaxies would be empty, but the James Webb Space Telescope found something else. A faint glow that was everywhere. It's not light from stars in known galaxies. Light from dust or noise from instruments isn't making it. An old hazy light that scientists have started calling ghost light has been seen but not explained. Its discovery has led to one of the strangest new ideas in modern cosmology, the idea that the universe is not really dark, even in its darkest places. This glow first came to attention when researchers subtracted every known light source from Webb's ultra-deep images. They meticulously removed stars from our galaxy, masked every visible galaxy, and corrected for instrument scatter and zodiacal dust from the solar system. Yet, even after all that, a soft, uniform brightness remained. It wasn't random background noise. Its distribution was statistically consistent across multiple deep fields. that meant it was real. Webb was seeing something diffuse, ancient, and everywhere. Earlier telescopes had hinted at this mystery. NASA's Spitzer Space Telescope and the New Horizons probe both detected an unexplained infrared background stronger than predicted by all known galaxies combined. But Webb, with its unprecedented resolution, turned suspicion into certainty. By resolving and subtracting individual faint galaxies that Spitzer couldn't, Webb reduced all known sources to below detection limits. And still, the ghost light persisted. So what could it be? The simplest idea is that this light comes from populations of ultra-faint galaxies just below Webb's detection threshold. Perhaps there are billions of tiny, dim star clusters spread through the cosmic web, too small to appear as distinct sources. But this explanation faces a problem. The spectral shape of the glow doesn't match the expected output of such galaxies. It's smoother, redder, and oddly featureless, more like the uniform glow of background radiation than the combined light of many discrete objects. A further theory says that the ghost light comes from intracluster stars, which are single stars that are thrown into space between galaxies by their own gravity. These orphan stars move around in galaxy groups without a home, but they still shine dimly. Hubble hinted at them in the past with microlensing effects, but the total infrared glow Webb sees can't be explained by how bright they are altogether. They just don't have enough of them. Some researchers think this diffuse glow could be fossil light, radiation left over from structures that no longer exist. Imagine galaxies or stellar populations from an earlier cosmic cycle, whose light has been stretched and dimmed beyond recognition by countless billions of years of expansion. In this scenario, Webb isn't just seeing across space, it's seeing across time boundaries, picking up the lingering photons of a universe long gone. This interpretation aligns eerily with certain cyclic or bounce cosmology models, in which remnants of an older universe bleed into ours through the cosmic background. The ghost light would then represent the dying embers of that predecessor cosmos. To test these ideas, astronomers compared the spatial pattern of the glow to the large-scale structure of the universe, the cosmic web of filaments and voids that connect galaxies. If the ghost light were just from faint galaxies, it should cluster along those filaments. But Webb's data shows a more even spread, suggesting it might fill space itself rather than tracing structure. This is precisely what one would expect if the light originated from ancient, decayed photons, a relic field rather than a population of current sources. Other explanations dip into even more exotic physics. Some propose that dark matter decay could be responsible. Certain theoretical dark matter particles might slowly annihilate or transform into low-energy photons over cosmic timescales, producing a weak, diffuse background glow. This process would occur everywhere dark matter exists, meaning everywhere, creating a nearly uniform infrared haze exactly like what Webb sees. If confirmed, this would be the first observational evidence that dark matter isn't completely dark after all. Whatever the origin, the ghost light presents one of the most profound puzzles of Webb's mission. It forces astronomers to rethink the balance sheet of the universe's light. For decades, scientists believed they could account for every photon, the cosmic microwave background from the Big Bang, starlight from galaxies, and radiation from interstellar dust. But Webb has revealed a missing component, a hidden energy reservoir that doesn't fit into any category. Quantum tunneling cosmology. The James Webb Space Telescope has solved a lot of mysteries, but they all lead to the same scary conclusion. The Big Bang might not have been the start of everything, but rather the end of something else. A very interesting theory that tries to explain this kind of change is quantum tunneling cosmology. This is a model that combines quantum physics and general relativity to explain how the whole universe could tunnel into existence from a quantum state that was already there. The most interesting thing about Webb's findings is how well they fit with that idea. Quantum tunneling is a well-understood phenomenon in particle physics. It happens when a particle passes through a barrier it classically shouldn't be able to cross, like an electron escaping a potential well even when it doesn't have enough energy to climb out. In the quantum realm, probabilities allow the impossible to happen occasionally. Now, imagine scaling that process up, not to an atom, but to the entire universe. In quantum cosmology, space itself could exist in a false vacuum state, a kind of metastable energy field. Eventually, a fluctuation could make a tiny region of that vacuum tunnel into a lower energy state, creating a bubble of expanding space. That bubble is what we experience as our universe. For decades, this concept was largely theoretical, a mathematical curiosity in equations by Alexander Vilenkin and Andrei Linde in the 1980s. But Webb's observations, galaxies forming impossibly early, mature elements where none should exist, and ghost light that might predate the Big Bang, have given physicists reason to revisit it. If the Big Bang was the result of a quantum tunneling event, it might explain why the universe looks so uniform, yet holds subtle asymmetries that seeded stars and galaxies. It could also explain why certain relics, like heavy elements or black holes, appear to have existed before our timeline began. Here's how it works. Imagine an eternal, high-energy quantum field, sometimes called the multiverse vacuum, bubbling with random fluctuations. Each fluctuation can, in theory, tunnel into a new state, birthing a separate region of space-time with its own physical constants. Most bubbles vanish instantly, but one, ours, inflated rapidly, cooled, and became stable. From our perspective, that inflation looks like a Big Bang. From a higher perspective, it was just a phase change, one of countless transitions happening across a cosmic sea of possibilities. The connection to Webb's data lies in what comes after that tunneling. If the transition wasn't perfectly smooth, fragments of the previous vacuum state could have survived. Energy fields, particles, or radiation patterns inherited from before the tunneling event. These remnants would act as cosmic fossils, showing up as faint excess energy, early heavy elements, or unexplained structure in the earliest galaxies. Webb's observations match those anomalies precisely. Some galaxies appear older than the Big Bang, others contain metals too soon, and everywhere Webb looks, it finds uniform background light just slightly brighter than expected. All of these could be the observational fingerprints of a quantum tunneling birth. The theory also offers a new way to think about cosmic inflation, the rapid expansion that smoothed the early universe. If inflation was triggered by tunneling, then each bubble of space could have expanded at slightly different rates, leading to observable variations in cosmic structure. In this view, Webb's discovery of galaxies appearing earlier and more massive than predicted may indicate that our bubble inflated unevenly, leaving behind regions that retain traces of the prior quantum field. Quantum tunneling cosmology doesn't require a before time in the classical sense. Instead, it describes a timeless quantum state, a condition of pure potential. Space, time, and energy weren't yet defined, only probabilities. When tunneling occurred, those probabilities collapsed into a specific configuration, our universe. But if tunneling can happen once, it can happen again, endlessly. That means Webb's telescope might not just be showing us ancient galaxies, it could be showing us the residual energy of other universes that never fully disconnected from ours. Some people disagree with these ideas and say that they are very hard to test. We can't see things outside our world, after all. Scientists have still been trying, though. Webb sees a dim, even infrared glow that could be leftover quantum energy leaking through the event's boundary. This is called ghost light between galaxies. In the same way, tiny linear imbalances in the cosmic background radiation, called anisotropies, might show how gravity affects our bubble and those nearby. If those were proven to be true, they would be the first real evidence of a multiverse, not just a theory. Additionally, the math seems to fit amazingly well. According to quantum tunneling models, the universe starts out big enough to not fall apart, but small enough to be uniform. This is exactly what we see. They also naturally explain why the energy density of our universe is so perfectly balanced. It didn't come from chaos, but from the road with the least amount of energy. So the Big Bang wasn't just a chance event, it was the most likely quantum shift that could have happened. The bounce scenario. The field of cosmology has told a simple story for more than 100 years. The universe started with a single explosion called the Big Bang and has been growing ever since. What if that's not the whole story? What if there was failure before they grew? This is the idea behind the bounce scenario, which is one of the most interesting options to the standard Big Bang model. The James Webb Space Telescope's finds have even brought this idea back to life, which was a surprise. The bounce hypothesis proposes that the universe didn't emerge from nothing, but from the ashes of a previous cosmos. In this model, the universe expands, slows, contracts, and then bounces into a new cycle of expansion, like a heartbeat on a cosmic scale. Each cycle wipes away some traces of the old universe, but not all. Tiny remnants, matter, radiation, even black holes, can survive the transition, seeding the next universe with structure. That might sound abstract, but Webb's early observations have made this idea harder to ignore. When Webb captured images of galaxies that seemed impossibly mature, massive, and chemically enriched within only a few 100 million years of the Big Bang, scientists realized the standard timeline couldn't explain such rapid development. There simply hadn't been enough time for so many stars to form, die, and recycle their materials. But in a bounce cosmology, those galaxies may not have started from scratch. Instead, they could be built from leftover matter, relic dust, compact stars, or primordial black holes, surviving from a previous cosmic cycle. This framework elegantly resolves several paradoxes. It explains why the early universe already contains heavy elements, why massive black holes appear too soon, and why the cosmic background radiation is so smooth, yet slightly irregular. In a bounce model, energy and information from the collapsing phase are compressed to Planck-scale densities, and then released during the next expansion, imprinting the new universe with faint memories of the last one. Webb's detection of excess infrared background light, the ghost glow that lingers between galaxies, may be a direct glimpse of that memory, fossil photons from a universe that came before ours. Physicists have developed multiple mathematical versions of the bounce scenario. The most prominent is the ikperotic model, first proposed by Paul Steinhardt and Neil Turok in the early 2000s. In their view, our universe's Big Bang wasn't a singular explosion, but the result of two higher-dimensional brains colliding in a larger multi-dimensional space. The collision generated the heat and energy of the Big Bang, while also carrying over imprints, gravitational waves, density variations, or even black holes from previous cycles. The theory predicts precisely the kind of faint but structured background fluctuations Webb and Planck have both observed. The loop quantum bounce is a different form that comes from the idea of quantum gravity. It seems to say that as the old universe shrunk, space-time itself became quantized or split up into tiny loops. Gravity changed from pulling things together to pushing them apart when density hit the Planck limit. This stopped a singularity from forming. The universe bounced or grew bigger again. This model says that things left over from the last contraction, especially small objects like black holes, might be able to live and show up again in the next cycle. It fits this theory perfectly that Webb found huge black holes less than 500 million years after the Big Bang. If true, it also explains the otherwise impossible uniformity of the cosmic microwave background, CMB. Rather than an outcome of inflation alone, that smoothness could result from information carried across the bounce. Even the tiny anisotropies, the small ripples of density, might be the fingerprints of the previous universe's final collapse. Those ripples then seeded the galaxies we see today. When inflation isn't enough. The inflation theory has been taken as truth for a long time in modern astronomy. It says that in the very first trillionth of a second after the Big Bang, the universe went through a burst of exponential expansion, stretching faster than light and smoothing out any bumps along the way. This made the way for the structure of the universe we see today. Inflation explained why the universe looks so uniform, why the cosmic microwave background is almost the same in all directions, and why space is flat in a geometric sense. The theory seemed invincible for decades, like it had a beautiful answer to almost everything. Inflation assumes that after this ultra-fast growth phase ended, matter cooled and gradually condensed into the first stars and galaxies. There should have been a long, quiet, dark age between the initial expansion and the ignition of light. Yet Webb's deep field surveys have found fully formed galaxies, supermassive black holes, and even heavy elements appearing far earlier than inflation models allow. If the universe expanded so violently at the beginning, smoothing out all density fluctuations, how did it build complex structures so quickly afterward? It's like watching a film of cosmic evolution on fast forward. The universe seems to have skipped entire chapters. To make sense of this, cosmologists began running simulations that adjusted inflation's parameters. More energy here, less there. Different, slow-roll conditions for the inflaton field that supposedly drove the expansion. None of them worked. The galaxies Webb found at redshifts above 12, meaning they existed less than 400 million years after the Big Bang, were still too massive, too bright, and too chemically evolved. Inflation simply didn't leave enough time for them to exist. Some people think that inflation happened more slowly, or not at all the way we think it did. In this multi-phase inflation theory, the universe may have gone through several bursts of faster expansion, each caused by changes in the quantum vacuum below. The strength and length of these bursts could have changed, making areas that were a little thicker or older than the rest. These areas could help explain Webb's impossible galaxies, which are places where stars started to form before the rest of the universe even cooled down. Another hypothesis is that inflation wasn't a single event, but rather a process that went on all the time in many universes. This model says that the world we can see is just one bubble in a very large sea of space. Each bubble is made by random changes in the space-time fabric. Webb's finding of weak background irregularities, like the extra ghost light and infrared radiation that doesn't fit our models, could be indirect proof that nearby bubbles are affecting ours. When two worlds meet, their energy fields may interact in a subtle way, warping light and starting the formation of structures before they are ready. Still others suggest that inflation never happened, or at least not in the way classical theory describes. Quantum gravity models, such as the loop quantum bounce, propose that what we call inflation was actually the rebound of a previous universe collapsing. The smoothness we attribute to inflation could instead be the residual order from that earlier cosmos. That would mean Webb's early galaxies aren't anomalies, they're expected. They were seeded by the memory of a previous contraction, not created from random fluctuations in a vacuum. Webb's findings also pose a deeper challenge. If inflation was real, it should have produced a very specific pattern of gravitational waves, ripples in space-time frozen into the cosmic background. So far, no telescope or detector, including Planck or BICEP 2, has found definitive evidence of those primordial waves. Webb, while not built for that purpose, has indirectly tightened the constraints by showing that early cosmic conditions were too orderly for the violent chaos inflation predicts. The silence of the sky, in this case, speaks volumes. Another problem is the Hubble tension, which is the ongoing argument between different ways of measuring how fast the universe is expanding. If you believe in inflation, that rate should be exactly right, but Webb's improved distance and redshift numbers only make the problem worse. We would expect all parts of space to grow at the same rate if inflation were global and constant. Observations now point to local differences, with faster expansion here and slower expansion there. It's as if the universe's growth still shows the effects of uneven starting conditions. Some cosmologists think that these signs point to more strange ideas, such as emergent spacetime, which says that inflation wasn't a burst in space, but the birth of space itself from a deeper quantum network. From this point of view, time and growth are just results of a deeper process that might happen again or change. The fact that Webb found smooth but slightly uneven galactic patterns could be a sign of that underlying grid showing up in the data. The forgotten universe. For most of modern history, the Big Bang has been the final limit, the point beyond which people can no longer understand anything. That model says that time, space, and matter all started around 13.8 billion years ago, growing from a point that was infinitely thick to become the universe we live in now. But as the James Webb Space Telescope keeps gathering information, that line that was once clear is beginning to fade. Webb's infrared eyes are finding signs of structure, light, and chemical complexity that shouldn't be there so soon after the Big Bang. To make sense of these new findings, some cosmologists have brought back an old idea. Maybe our universe isn't the first. It's possible that we live in the shadow of a world that no longer exists. The concept isn't new. Ancient philosophers imagined eternal cycles of creation and destruction. Modern physics, however, grounds the idea in mathematics. If time didn't truly begin at the Big Bang, then our universe may be one iteration in an endless chain, each born from the remnants of the last. The most developed form of this hypothesis is conformal cyclic cosmology, CCC, proposed by Nobel laureate Roger Penrose. In CC, the universe expands indefinitely, and as it does, all massive particles decay. Black holes evaporate, matter disintegrates, and only radiation remains. Eventually, after countless trillions of years, the universe becomes smooth, empty, and timeless. At that point, something remarkable happens. Without mass, there's no meaningful scale of time or space, and the infinitely stretched cosmos becomes mathematically indistinguishable from a new Big Bang. A fresh universe begins. Penrose predicted that if this were true, the cosmic microwave background, the oldest light in our observable universe, should still bear faint imprints of the previous cycle. He called them Hawking points, circular patches slightly warmer than their surroundings, remnants of black holes evaporating in the prior eon. For years, these patterns were debated, with data from the Planck satellite offering tantalizing but inconclusive hints. Now, Webb's ultrasensitive infrared data have given this theory new relevance. The faint background irregularities and unexplained ghostlight that Webb observes might be the very relics CCC predicted, the dying radiation of a universe that came before ours. Even Webb's early galaxy data fit the pattern. If matter survived across cycles, carried forward as compressed relics or quantum seeds, then it would explain why the first galaxies in our universe appear pre-enriched with heavy elements. Those elements wouldn't have needed to form anew. They would be the recycled ashes of a prior cosmos. Similarly, the discovery of supermassive black holes only a few 100 million years after the Big Bang could make sense if those objects are ancient survivors, black holes that persisted through the bounce and re-emerged in the new expansion. Under this lens, Webb's deep fields aren't showing us cosmic infancy at all, but cosmic memory. Support for this cyclical idea also comes from the uniformity of the cosmic microwave background itself. In the standard inflation model, the universe's extreme smoothness is explained by a short burst of exponential expansion. But a previous universe that had already expanded to near-perfect uniformity before collapsing could produce the same effect. No inflation required. This would make Webb's observations not an anomaly, but a confirmation. The early universe looks too organized because it inherited that order. Critics argue that cyclic models shift, rather than solve, the problem of origins. If the universe repeats infinitely, where did the first one come from? Others point out that CCC and related models struggle to explain the observed abundance of dark energy. But supporters counter that dark energy could be the very mechanism driving the cycle. The repulsive force that stretches the universe into flatness also resets it for its next beginning. For Webb's observers, what makes this idea so compelling is how neatly it ties the telescope's discoveries together. The presence of ancient metals, mature galaxies, ghost light, and early black holes all fit into a narrative of continuity. Each piece suggests that something survived, that the Big Bang was less of a beginning and more of a handover. The effects are huge if the lost universe theory is true. In other words, time has been around for a very long time, not 13.8 billion years ago. Instead of being made, matter is constantly renewed by expanding and contracting. Even awareness, which is made up of the atoms in our brains, would be made up of parts that have lived many lives in other universes. Older worlds are buried in the sky, and their light is stretched thin but not gone. Testing such an idea is difficult, but not impossible. Scientists are now analyzing Webb's deep field mosaics for the kind of faint concentric patterns Penrose predicted, subtle rings or gradients invisible to older instruments. Gravitational wave observatories may also help. A cyclic universe could leave residual echoes in space-time that repeat at predictable frequencies. If such evidence emerges, it would mark a turning point in cosmology as profound as Einstein's theory of relativity. Cosmic dust older than time. Dust. It doesn't sound like the key to changing the course of time in the universe. On the other hand, dust is everything in science. It is what stars are made of, what planets are made of, and what holds life together chemically. Scientists knew something strange was going on when the James Webb Space Telescope found cosmic dust in parts of space where it shouldn't have been there because the space was so new. Not yet. That dust wasn't meant to be there. It could be older than time itself. To grasp why this is so shocking, we need to understand how cosmic dust forms. After the Big Bang, the universe was almost entirely hydrogen and helium, with only trace amounts of lithium. Heavier elements, carbon, silicon, iron, are necessary for dust, and those are created inside stars through fusion and spread by stellar death. It takes generations of star formation and destruction to build up enough heavy elements to make grains of dust. In theory, that process couldn't begin until at least 600 million years after the Big Bang. But Webb has upended that timeline completely. Its infrared instruments, especially MIRI, Mid-Infrared Instrument, have detected vast amounts of dust in galaxies that existed only 300 million years after the Big Bang, far too early for multiple stellar generations to have created it. In some cases, the dust abundance rivals that of modern galaxies like the Milky Way. That shouldn't be possible. The universe at that time should still have been pristine, too young and too simple for this kind of chemical maturity. Astronomers first encountered this mystery in 2023, when Webb observed galaxies like Glass Z12 and Jade's GS Z11-0, whose spectra revealed the presence of carbonaceous grains and silicate compounds, the same kinds of dust found in later evolved galaxies. Even more puzzling, the light absorption patterns suggested grain sizes comparable to those produced by supernova explosions, meaning the dust had already been processed and recycled. Yet, there hadn't been enough time for the first stars to form, die, and create such debris. Where did it come from? Population 3 stars, which are thought to be the first generation of huge stars that don't have any metals, could be one reason. These huge objects may have lived quickly and died young, exploding just a few million years after they were formed and spreading dust before anyone thought they would. But Webb's data makes that idea less clear, because it hasn't found a single clear population 3 signal yet. Webb sees galaxies that already have metals and complex chemicals in them, which suggests that these stars weren't even the first ones. That led some researchers to propose that the dust didn't originate within our own cosmic cycle. Instead, it may be pre-Big Bang dust, remnants of matter carried over from a previous universe. In a cyclic or bounce cosmology, where universes collapse and re-expand infinitely, some dense particles could survive the transition, compressed but not destroyed. When our universe began expanding, that ancient material could have seeded the formation of new galaxies, giving them a head start. This theory fits several clues in Webb's data. The dust it detects appears unusually mature, containing a mix of carbon-rich and silicate materials that would normally require multiple stellar generations to produce. It's also distributed more evenly than expected, filling intergalactic space instead of being confined to young galaxies. That uniformity suggests an origin older than any star, a primordial dust bath inherited from before the Big Bang. To test this, astronomers compared Webb's observations to data from ALMA, the Atacama Large Millimeter Submillimeter Array in Chile. ALMA had already detected coal dust in distant galaxies, but couldn't determine its exact composition. Webb's infrared precision allowed researchers to identify specific spectral lines, confirming not only the presence of complex molecules, but also their temperature and structure. The grains appear to have been processed, heated, cooled, and recondensed more than once. That's an evolutionary history too long for the available time since the Big Bang. Dust is very important for keeping the temperature stable and starting the process of star creation. If there was a lot of dust back then, it means that the first stars and galaxies didn't form from clouds of pure hydrogen, but from gas that was rich in dust and collapsed more easily under gravity. That might explain why Webb finds big, well-organized galaxies so soon after what he thinks is the beginning of time. The dust wasn't just a strange thing, it was speeding things up. Some physicists have speculated that dark matter itself could decay or interact with normal matter in a way that produces dust-like particles. In that case, Webb's observations might be the first indirect evidence that dark matter is not entirely inert. Such a process could continuously replenish cosmic dust from the invisible sector of the universe, giving rise to the widespread glow Webb sees between galaxies. The photon fossil test. So far, everything the James Webb Space Telescope has found, galaxies that look too big, elements that are too old, and too much dust, points to one disturbing question: what was there before the Big Bang? Some cosmologists have come up with the idea of looking for photon skeletons, which is so vague and far-fetched that it almost sounds like science fiction. In the scientific sense, these are not fossils. Instead, they are old bits of light that may even be from before our world. And if Webb or later missions can find them, they would be the first clear proof that the Big Bang wasn't the start, but rather a part of a much bigger story in the universe. Photons, the fundamental quanta of light, are among the most enduring particles in existence. Unlike matter, which can decay or transform, photons travel unimpeded across the expanding universe, their wavelengths stretched by cosmic expansion, but their identity intact. The cosmic microwave background, CMB, is made of such photons, released when the universe was just 380,000 years old. But what if some photons were even older, remnants of a universe that existed before the CMB, before space and time as we define them? If those ancient photons somehow survived the transition from a previous cosmic cycle into ours, they would still be here, embedded in the faint background radiation we see today. That's the essence of the photon fossil test. The idea that traces of pre-Big Bang light might still be measurable, hidden within the radiation fields Webb and other observatories detect. In practical terms, scientists are looking for subtle deviations in the energy spectrum of the CMB and the cosmic infrared background, CIB, that can't be explained by known astrophysical sources. These deviations, called spectral distortions, could be the fingerprints of ancient photons that entered our universe already redshifted beyond anything the Big Bang could produce. The concept began taking shape in the 2010s, when theorists working on cyclic and quantum cosmologies suggested that if universes repeatedly collapse and re-expand, some photons could tunnel through the bounce. During such transitions, space-time doesn't vanish completely. Instead, its quantum structure contracts, compresses, and re-expands, preserving certain energy modes. Those modes would re-emerge in the next universe as extremely low-frequency radiation, too faint for most telescopes to detect. But Webb, designed to capture infrared wavelengths with unprecedented precision, might already be glimpsing their faint echoes. When Webb measured the diffuse infrared background, the ghost light lingering between galaxies, it found an unexplained excess of photons. They're not from stars, not from galaxies, and not from any known cosmic dust. Their spectrum is smoother than expected, lacking the usual peaks of stellar radiation, and stretches across multiple wavelengths in a way that matches predictions for fossil photons from a pre-Big Bang epoch. Some researchers have called this discovery a possible signal of relic light. Others remain cautious, arguing that it could still come from unaccounted intergalactic dust. But the match to theoretical models is uncanny. To isolate such photons, astronomers analyze the brightness temperature of the cosmic background, a measure of how intense the radiation appears at different frequencies. If some of that radiation doesn't follow the expected Planck distribution, the perfect blackbody curve of the Big Bang's afterglow, then it might be fossil light bleeding through. Even a distortion of 1 part in 100,000 could be significant. Instruments like Kobe and Planck were too limited to detect such fine differences, but Webb's deep infrared spectrographs can measure them with exquisite precision. It would be a big deal if fossil photons were proven to exist. They would mean that radiation and energy are not made in each cosmic cycle, but are instead kept the same and sent from one world to the next. That would mean that the multiverse's total energy never changes, even though different worlds grow, fade, and die. Also, it would explain why the world seemed to turn on so quickly after the Big Bang. Based on Webb's early data, those photons would have been like seeds, reionizing hydrogen and starting the first chemical processes almost right away. Many naysayers say that finding photons from before the Big Bang is almost impossible. They have wavelengths that are so long and energies that are so low because of the growth of the universe that they are almost impossible to tell apart from thermal noise. Even Webb's tools might not be able to clearly tell them apart. But scientists are already working on replacements that might be able to do it. Plans for missions like the Primordial Explorer, PIXI, and the Spectral Distortion Mapper would make it 100 times easier to measure the CMB's spectrum and find the distortions left behind by photon fossils. There's also the matter of polarization. Fossil photons, having traveled through multiple universes or quantum transitions, would likely have a unique polarization pattern, one that doesn't align with the ordinary E-mode or B-mode polarization produced by inflation. If such a pattern were found, it would constitute smoking gun evidence for a pre-Big Bang signal. Several teams are already examining Webb's polarimetric data for anomalies, though none are yet conclusive. Hidden dimensions theory. The universe has 4 dimensions, 3 of space and 1 of time. This has been known to scientists for more than 100 years. That theory is a good fit for everything, from the paths of planets to quantum particles. But when the James Webb Space Telescope started looking into the farthest corners of space and time, it started coming back with data that didn't quite fit. There are small signs that the universe may be formed by forces from outside our visible world. For example, galaxies are growing too quickly, gravity is working too well, and light is bending more than it should. The idea comes from theoretical physics, even though it sounds crazy. It's called the hidden dimensions theory, and Webb could be the first tool that can pick up on its clues. The concept emerged from attempts to unify quantum mechanics with Einstein's general relativity. In the 1920s, German physicist Theodor Kaluza proposed adding a 5th dimension to spacetime to reconcile electromagnetism and gravity within a single framework. The idea was radical, but mathematically elegant. It worked, but only if the extra dimension were curled up so tightly that we couldn't detect it. Later, this concept inspired string theory, which posits that all fundamental particles are actually tiny, vibrating strings existing in up to 10 or 11 dimensions. Most of these extra dimensions, according to theory, are compactified, folded into sizes smaller than an atomic nucleus. They remain hidden, influencing reality indirectly by determining the constants of nature. But if these dimensions are truly there, their effects should sometimes leak into the observable universe, particularly in the most extreme environments. And that's exactly what Webb is revealing. When the telescope looked at the early universe, It found galaxies assembling and rotating in ways that defy the gravitational limits of four-dimensional space-time. For example, Webb's measurements of galactic spin rates in some high redshift galaxies show velocities too high for their visible mass to explain, even accounting for dark matter. One possibility is that gravity behaves differently at cosmological scales, perhaps because it's not confined to three spatial dimensions. In a higher dimensional universe, gravity could spread through the bulk, the full higher dimensional space, weakening more slowly than expected and accelerating structure formation. This might be why the first galaxies in Webb's images appear far more massive and orderly than standard physics allows. Another clue comes from gravitational lensing, the bending of light around massive objects. Webb has detected lensing effects that are slightly stronger and more frequent than models predict. In one case, light from a distant quasar appeared bent by an invisible structure with no detectable matter present. Some theorists argue that such discrepancies could arise if space itself is warped by hidden dimensions, subtly altering the paths of photons as they move through it. This warping could even explain the mysterious dark energy driving cosmic expansion. Rather than being an unknown force, it might be the geometric influence of higher dimensional curvature bleeding into our 4D universe. One of the most captivating concepts is that these extra dimensions might help explain what dark matter is. If gravity can reach into dimensions that we can't see, it could cause localized changes called gravitational wells that look like the mass of matter we can't see. In this case, what we call dark matter might be a form of geometry, places in the universe where gravity leaks out into the mass and then loops back around. Webb's early results, which show gravitational behavior that doesn't match up with what we know about baryonic mass, gives us tempting hints in this direction. The idea of extra dimensions also dovetails with brane cosmology, a branch of string theory that envisions our universe as a three-dimensional brane floating in a higher dimensional space. Collisions or interactions between branes could produce phenomena that look like Big Bangs, explosive bursts of energy that give birth to new universes. Some of Webb's findings, such as the apparent existence of structure and light before the classical Big Bang timeline, fit surprisingly well with this view. If our brane collided with another in the distant past, the resulting energy transfer could have jump-started our cosmic expansion while leaving behind residual distortions, faint uniform backgrounds of radiation, like the ghost light Webb keeps detecting. How could we test any of this? The key lies in precision. Extra dimensions would subtly modify the behavior of gravity and light. For instance, certain wavelengths of radiation might be redshifted slightly differently depending on how photons travel through warped geometry. Webb's infrared spectra are detailed enough to spot such anomalies, and indeed, a few candidate signals already show small but consistent deviations from the predictions of four-dimensional models. These could be calibration errors, or they could be whispers from the higher dimensional architecture of reality. Theoretical physicists are already comparing Webb's data to ADAS-CFT and Randall-Sundrum models, mathematical frameworks that describe how gravity behaves if our universe is embedded in a higher dimensional bulk. In these models, extra dimensions can create small corrections to the cosmic expansion rate and the distribution of galaxies. Intriguingly, some of those corrections match the discrepancies Webb has found between predicted and observed galaxy clustering. Gravitational wave archaeology. When Albert Einstein forecast gravitational waves in 1916, he thought they would come from huge events like stars hitting, black holes merging, and even the heartbeat of gravity. In 2015, 100 years later, the LIGO detector found those waves for the first time, showing that Einstein was right. But the James Webb Space Telescope is helping cosmologists see that gravitational waves could also be fossils, or time boxes, from before the first stars formed. They might hold the key to the oldest story in the universe, what happened before the Big Bang. This emerging field is called gravitational wave archaeology, the attempt to reconstruct cosmic prehistory by decoding the faint gravitational ripples still reverberating through space. The concept rests on a simple but powerful idea. If gravity was active before the Big Bang, then its waves might have survived the transition into our expanding universe. Unlike light, which can be scattered or absorbed, gravitational waves interact so weakly with matter that they could pass unaltered through cosmic collapses, bounces, or even quantum transitions between universes. In other words, while photons fade and atoms decay, gravity remembers. The problem has always been detection. Modern instruments like LIGO and Virgo can hear waves from stellar events billions of light-years away. But those signals are relatively recent, coming from the last few billion years. The ancient waves cosmologists are after are far subtler, with wavelengths spanning entire galaxies. They're too long and too faint for ground-based detectors to capture. But space-based missions like LISA, Laser Interferometer Space Antenna, planned for the 2030s, will finally be able to sense them. And Webb is already helping scientists figure out where to look. By mapping the large-scale structure of the early universe, Webb is essentially tracing the fingerprints gravitational waves left behind. Tiny irregularities in the distribution of galaxies, slight clustering here, unusual voids there, could be the frozen imprint of gravitational ripples stretching space during the first moments of creation. When Webb measures the shapes and positions of galaxies at redshifts above 10, it's reading the record of those ancient oscillations. Some regions appear ever so slightly elongated or magnified, patterns consistent with space-time having been stretched by gravitational waves billions of years ago. If confirmed, these would be the first indirect detections of primordial gravitational waves, echoes from an era earlier than any light can reach. And what's truly exciting is that these waves could test which cosmological model is correct. The standard inflationary theory predicts a smooth Gaussian spectrum of gravitational noise. A bounce or cyclic universe, on the other hand, would produce sharp periodic ringing, a resonance left over from the universe's previous contraction. If Webb's data shows those periodicities, it would be direct evidence that our universe has lived and died before. Webb's role is unique. While it cannot detect gravitational waves directly, it reveals their effects through what physicists call tensor imprints, subtle distortions in light patterns caused by ancient gravitational perturbations. When Webb observes the faint shapes of galaxies or the polarization of infrared light across cosmic filaments, it's essentially seeing how space-time has been gently tugged over billions of years. Combine those measurements with upcoming data from LISA, and scientists can perform true gravitational archaeology, reconstructing the timeline of gravitational activity all the way back to, and possibly before, the Big Bang. Some of Webb's earliest deep field maps show slight alignments of galaxies that standard dark matter simulations can't explain. These alignments occur over scales of hundreds of millions of light-years, suggesting that something once rippled through that space, stretching it uniformly. Moreover, certain temperature variations in the cosmic infrared background detected by Webb appear to correlate with older anomalies found in the cosmic microwave background. The overlap is small but suggestive, as if both datasets are seeing the same ancient gravitational fingerprint from two different eras. If those patterns are correct, they would be the first fossil proof of gravity before the Big Bang. This gravity would have been a continuous thread that linked worlds as they went through cycles of falling apart and starting over. Waves like these might even help explain why the universe seems to be expanding at slightly different speeds in each direction. Astronomers are still trying to figure out what the so-called Hubble tension means. It's possible that old gravity ripples are still affecting space-time and could slightly change the way the universe is expanding. The potential payoff is enormous. By decoding these waves, scientists could determine whether our universe truly began from nothing or from a prior phase that contracted under gravity's pull. They could also measure how quantum gravity behaves under extreme conditions, a key step toward a unified theory of physics. In effect, gravitational wave archaeology would let us do something once thought impossible: observe before the beginning. To make this dream come true, scientists are now planning trips that will add to Webb's data. LISA will look for gravitational waves with a medium frequency that come from black holes colliding. Meanwhile, pulsar timing arrays, which are networks of closely watched neutron stars, are already showing signs of ultra-low frequency ripples that may be primordial. Together, these devices will give us a full picture of gravity history, from the newest parts of the universe to the first stirrings of it. Webb's beautiful infrared mapping will give them the framework, the exact locations of places in the past where space has been slightly twisted by forces that we can't see. Entropy's reversal. The second law of thermodynamics says that entropy, which is a measure of confusion, always goes up. This breaks every other law of physics we know. Stars die, galaxies spread out, and ice melts. People say that the end of the world won't be with fire, but with heat death, which means that everything will become cold. With the James Webb Space Telescope, however, we are seeing a puzzle that goes against this basic rule. In the early days of the universe, right after the so-called Big Bang, there seems to have been too much order. Galaxies formed too quickly, gas collapsed too quickly, and structure arose almost instantly from chaos. It's like chaos ran backwards at the beginning of time. This observation has reignited a bold idea among cosmologists. Maybe it did. Maybe the universe's arrow of time, the one that points from order to disorder, flips during certain cosmic transitions. If that's true, then what Webb is observing isn't a violation of physics, but evidence of a mirror phase, a moment when the universe briefly moved backward in entropy before expanding forward again. The concept sounds radical, but it's grounded in serious theory. In the 1970s, physicist Thomas Gold and later Roger Penrose proposed that entropy might not always flow in one direction across the entire multiverse. Instead, it could reset or even reverse during major cosmological events, such as a big bounce or a quantum tunneling transition between universes. In those brief instances, the future of one universe could become the past of the next, with entropy starting fresh. To observers within each universe, time would always move forward, but across the boundary, its direction could invert. This is where Webb's discoveries come in. The galaxies it sees only a few 100 million years after the Big Bang shouldn't be so organized. They show rotation, metal enrichment, and well-formed disks, qualities that should have taken billions of years of evolution. In thermodynamic terms, their entropy is too low. The cosmos looks young but behaves old, like a film rewinding faster than it should. To many researchers, this hints that the universe's entropy clock may have restarted at the Big Bang, or even ticked backward for a brief period before stabilizing. Webb's detailed maps of cosmic filaments, the huge structures that link galaxies and look like webs, are one of the best pieces of evidence. Cosmological models usually say that these strands formed over at least 1 billion years, but Webb has found them less than 500 million years after the Big Bang. Their regularity shows that the early universe wasn't just a bunch of random events. It was deeply organized, almost like it took on the structure of a previous cycle. If the patterns of order from a falling universe were fed into the next expansion, entropy might seem to reset, while memory is kept. This would create the kind of symmetry that Webb now sees. The mathematics of entropy reversal finds support in CPT symmetry, a principle of particle physics stating that the laws of physics remain consistent if you simultaneously flip charge, c, parity, p, and time, t. Some cosmologists have suggested that the Big Bang created not one universe, but two, our universe expanding forward in time and a mirror universe expanding backward. From our perspective, that twin cosmos would appear to evolve in reverse, its entropy decreasing as ours increases. Each universe would see itself as moving forward, but from a higher perspective, they'd be time reflections of each other, balancing the total entropy of the multiverse to zero. If that sounds vague, Webb's data might give you real proof. Small differences in the polarization of background light, the even spread of heavy elements, and the way galaxies are lined up all point to an early universe that was too uniform. This is a sign that our universe may have been paired at birth with another one that was growing in the opposite direction of time. Both of them, working together, would keep the basic symmetry of physics and let entropy grow properly in each world. There is also a deep intellectual meaning. If entropy can go backwards, then the Big Bang wasn't an explosion of chaos. It was a change of phases that led to new order. It wasn't chaos at the start of the universe, it was rebirth. That was when the thermodynamic arrow turned around. From the first atoms to the start of life, everything that happened after that happened under a new clock of time. Webb sees smoothness in early galaxies, which might not be a strange thing. It could be the physical memory of that change. The primordial black hole link. One thing that James Webb has shown over and over again is that the early universe was full of black holes, and not just small ones. Webb has found supermassive black holes at the centers of galaxies. This happened less than 500 million years after the Big Bang, when stars should have just started to form. The rules of astronomy say that these huge objects shouldn't exist yet. They didn't have enough time to grow from stars that were falling. If they didn't form after the Big Bang, then the next question that makes sense is whether they could have formed before it. That's where the theory of primordial black holes, PBHs, comes in. An idea now finding fresh life in the age of Webb. PBHs are hypothetical black holes that originated not from stars, but from the high-density fluctuations in the universe's first moments. Or, as some cosmologists now suggest, from a prior cosmic cycle. They would have been born seconds, or perhaps before seconds existed, after the universe began expanding, forged from regions where gravity briefly overpowered everything else. These ancient black holes would predate galaxies, stars, and even atoms, making them the oldest structures in the cosmos. For decades, primordial black holes were mostly theoretical, thought to have evaporated quickly via Hawking radiation. But Webb's deep field data has reawakened the idea because of one striking observation. There are too many massive black holes too early. Galaxies that should be tiny seedlings already host cores weighing millions or even billions of solar masses. To create them through normal processes, black holes would need to accrete gas at impossible speeds or merge far more efficiently than physics allows. That mismatch has turned PBHs from a fringe theory into a serious contender. In this model, primordial black holes acted as cosmic seeds, gravitational anchors around which matter condensed, giving birth to the first galaxies. Instead of galaxies forming first and then creating black holes, it may have been the other way around. This idea explains several of Webb's puzzles at once. The early presence of large, well-structured galaxies, their extraordinary compactness, and the mysterious correlation between galaxy mass and central black hole mass, even in the earliest epochs. PBHs could also account for dark matter, the invisible mass that makes up most of the universe's gravitational pull. If enough small PBHs were produced in the early universe or survived from a prior one, their collective gravity could mimic dark matter's effects. Webb's measurements of galactic rotation curves and gravitational lensing patterns have hinted at mass distributions that could fit this model. Some regions show slightly clumpy gravitational fields, inconsistent with smooth dark matter halos, but consistent with a granular population of compact objects, perhaps PBHs scattered throughout space. To test this, scientists are looking for indirect clues. When two black holes merge, they release gravitational waves. A universe seeded with PBHs would have produced countless such mergers across cosmic history, leaving behind a constant gravitational wave background. The faint rumble recently detected by pulsar timing arrays, rhythmic signals from spinning neutron stars, might already be picking up that background. If confirmed, it would be the first evidence of a population of primordial black holes shaping the universe from its infancy. Some cosmologists even say that PBHs might have been around before the Big Bang, in a bounce cosmology in which the universe before ours contracted and then expanded. Dense leftovers like black holes might have been able to live. They would come back as seeds in the new cosmos when the new growth started. This would explain why Webb sees black holes so soon after time is said to have started. They didn't form after the Big Bang. They were there during it. So the Big Bang wasn't a start, it was a recycling. The birth of a universe that was already full of gravity ghosts from long ago. The idea also fits beautifully with Roger Penrose's conformal cyclic cosmology, which predicts that black holes from one universe evaporate into radiation that seeds the next. The final evaporation bursts from those black holes. Hawking radiation at unimaginable energies could trigger quantum fluctuations that form new PBHs after the next bounce. In this grand cycle, black holes are both the undertakers and the midwives of creation. They end one universe and begin another. Webb's observations of early quasars strengthen the case. Some quasars, bright beacons powered by accreting black holes, are visible at redshifts above 10, meaning their light began only a few 100 million years after the Big Bang. Their sheer brightness implies black holes with masses exceeding 1 billion suns. No known process could create them so quickly unless they began as colossal seeds, precisely what PBH models predict. Some people say it will be very hard to prove that primordial black holes exist. Webb can't see them directly. All he can see is how their gravity affects him. But every new observation, every galaxy that seems to be fully grown for no reason, every strange gravitational lens, and every early quasar makes the case stronger. More and more, the easiest answer is that some of the oldest black holes in the universe were never young. False Big Bang? According to scientists, the universe started with a violent growth called the Big Bang. This idea has been supported by Edwin Hubble's discovery that galaxies are moving quickly away from us. Since then, every discovery, like the cosmic microwave background, the redshift of galaxies, and the fact that light elements are very common, seem to support that idea. It became the most important thing in astronomy. Now that the James Webb Space Telescope has shown us galaxies, black holes, and even chemical structure much earlier than they should have, an interesting idea has come up again. What if the Big Bang we know wasn't really the beginning, but just a local event, one bubble of creation among many? To put it another way, what if the Big Bang in our world was a fake one? This idea doesn't deny that an explosion-like expansion occurred. Rather, it questions whether it was the singular beginning of all space and time. In some cosmological models, especially those inspired by string theory, the Big Bang is just one phase transition in a much larger, older cosmos. Space itself could be part of a vast multiverse foam, filled with countless expanding regions, each undergoing its own Big Bang-like burst. We see only the inside of our own bubble, but beyond its boundary, others might exist, older, newer, or already extinguished. The false Big Bang hypothesis first gained traction in the early 2000s under the eternal inflation model. Inflation, the rapid expansion that supposedly followed the Big Bang, may not have stopped everywhere at once. Instead, quantum fluctuations could cause different regions to keep inflating, spawning new pocket universes, like soap bubbles in a cosmic sea. Each bubble's interior becomes a universe with its own physical laws, constants, and histories. Our universe would simply be one of them. Not unique, not first, just one event in a much larger pattern. But Webb's discoveries give this old theory a startlingly fresh relevance. If our universe's Big Bang were merely one localized expansion inside a larger pre-existing space, it could explain why galaxies appear so mature so quickly. They might have inherited material, stars, dust, or even black holes, from the medium that surrounded our bubble before it inflated. Those pre-bubble relics could have drifted in through its boundary, appearing to us as impossible early structures. Webb's detection of heavy elements, complex dust, and massive black holes within a few 100 million years after the supposed beginning fits this picture disturbingly well. In this framework, the Big Bang was less a birth than a phase change, like water freezing or boiling. A patch of the cosmic field reached a critical threshold, triggering inflation and forming our observable universe. But the surrounding space, the multiverse background, might still exist, inflating endlessly or cycling through its own transformations. From that perspective, what we call the beginning is simply one thermal fluctuation in an infinite ocean of creation. The idea also offers a natural solution to one of cosmology's biggest puzzles, the cosmological constant problem: why the universe's vacuum energy is so small compared to quantum predictions. In a multiverse scenario, every bubble universe could have a different vacuum energy. We just happen to live in one where it's low enough for galaxies and life to form. Webb's data showing fine-tuned balance between matter density and cosmic expansion aligns with this selection effect. It's not that the universe was designed perfectly. It's that countless others weren't, and we're in one that worked. A false Big Bang could explain the strange uniformity of the early universe. The cosmic microwave background is almost perfectly smooth, with temperature variations of only 1 part in 100,000. Inflation theory accounts for this. But if our universe began as a bubble expanding into a pre-existing space already filled with radiation, that background could have been inherited, not created. The smoothness we see might belong to the environment outside our universe, bleeding through the boundary during its birth. Webb's infrared observations of faint uniform background light could be direct evidence of that inherited radiation. Unlike the cosmic microwave background, which comes from within our bubble, this faint glow could represent energy from outside, relic photons from older universes or regions still inflating nearby. Some physicists call this the bulk background, radiation that seeps into our cosmos from the larger dimensional framework in which it formed. The brain cosmology view adds one more thing to the picture. This idea says that the world is made up of a 3-dimensional brain that floats in a 4-dimensional space, the bulk. When 2 brains hit each other, they release a huge amount of energy. To people inside, this process looks exactly like the Big Bang. If these kinds of accidents happen over and over again in the past of the universe, each one would create a new universe while leaving the others alone. Webb's views of organized galaxies, mature dust, and old structures so soon after time, zero might have been leftover matter swept up by the collision itself, not matter appearing out of thin air. If the Big Bang was local, not universal, it might also explain why the laws of physics, so consistent within our cosmos, seem fine-tuned but arbitrary. They could be the result of conditions specific to our bubble's birth, its collision energy, its curvature, its starting field values. Other universes might operate under entirely different rules. Somewhere else, gravity might be stronger, time might flow differently, or matter might not exist at all. It won't be easy to prove this. The edge of our bubble, which is also known as the cosmic horizon, is the farthest thing that we can observe. We'll never be able to see straight through it, but Webb's data may already have secondary proof. Astronomers are looking for anisotropies, which are small linear patterns in the background light that might show gravity pull from beyond our universe. For example, a bubble impact would leave a weak circular mark in the cosmic microwave background or change the way galaxies are spread out in a way that can be predicted. Some of these trends have been possibly found in Planck's data, and Webb's more accurate infrared data could confirm them. The multiverse signature. For many years, the multiverse was only used in science fiction and late-night philosophy. It was a way for cosmologists to avoid reality when the mathematics got too weird. With the help of the James Webb Space Telescope, the word is now being used in serious science conversations. Webb's ultra-high sensitivity has found strange things that the standard Big Bang model can't explain. These include galaxies forming before they should, patterns in the cosmic background that shouldn't be there, and light that seems to come from nowhere. Some experts think that these strange events might be the first real signs that our universe is not the only one in the multiverse. In most versions of multiverse theory, our universe is one of countless pocket universes, each born through processes of inflation, quantum tunneling, or higher dimensional collisions. Each universe could have its own laws of physics, constants, and even numbers of dimensions. While we can't directly travel or communicate across these regions, they might still leave behind footprints, subtle distortions in cosmic structure, background radiation, or gravitational waves detectable within our own sky. Webb, designed to probe deeper into space and time than any telescope before, may already be seeing those footprints. A particularly strange thing that stands out is the small but measurable difference in how galaxies are spread out at very large distances. Cosmologists noticed that large-scale clustering looks a little heavier in one way than the other when they mapped Webb's early universe galaxies. The difference is very small, just a few percent, but it is statistically important. It matches earlier signs from the Planck satellite's data on the cosmic microwave background, which showed a cold spot and directional anisotropy that inflation couldn't explain. Some scientists think that these kinds of imbalances might be scars from when our universe and another one crashed into each other when they were very young. In the growing multiverse, if two bubble universes form close enough to each other, their spreading edges can bump into each other, creating a ring-shaped area of gravitational disturbance. From inside, that would look like a patch of sky that isn't lined up right, which is exactly what Webb and Planck see. The same idea could also explain the mysterious infrared ghostlight that Webb continues to detect between galaxies. If neighboring universes exist beyond our cosmic horizon, photons or gravitational energy from their boundaries could bleed into ours through quantum tunneling or brane interaction. This leakage light would appear uniform, directionless, and slightly redshifted, precisely the qualities of Webb's unexplained infrared background. If that glow is truly inter-universal radiation, Webb may have already glimpsed the light of another cosmos shimmering through the walls of our own. Another potential signature lies in the fine structure of physical constants. The strength of gravity, the charge of the electron, and the ratio of proton to electron mass are all remarkably fine-tuned for the existence of stars, chemistry, and life. The odds of those numbers being just right by chance are vanishingly small, unless there are countless universes with different parameters, and we inhabit the one where conditions permit observers. Webb's high-precision spectroscopy has found subtle deviations in elemental absorption lines from the earliest galaxies, hinting that fundamental constants may have been slightly different in the distant past. If confirmed, it would suggest our universe's physical laws have not been entirely uniform, that we might be seeing the edges of domains where neighboring universes influence ours through overlapping fields. Even the arrangement of cosmic voids and filaments, the great web connecting galaxies, offers clues. In a purely random inflationary expansion, the large-scale structure should be statistically uniform. But recent mapping from Webb's JADES and SEERS programs shows slightly repeating geometries in the spacing of early galactic clusters, as if the pattern were imprinted by standing waves in space-time. Some physicists propose that these could be interference patterns from nearby universes, gravitational echoes where two or more regions of the multiverse overlapped in their early growth. If such evidence holds up, it would lend weight to the eternal inflation model, a framework where inflation never fully ends but continues indefinitely, spawning new universes like foam on an infinite sea. Each bubble expands at light speed, separated from the others by vast inflating barriers. Yet under certain conditions, these barriers can thin or even rupture, allowing energy to leak between neighboring bubbles. The resulting distortions could produce exactly the kind of asymmetries Webb and Planck observe. Unbelievable claims need, of course, unbelievable proof. Most cosmologists are still careful because cosmic variance, which is the statistical noise that comes from looking at only one universe, can look like these kinds of trends. Webb's collections are still pretty new, and many of the deepest views it has made are of small parts of the sky. It will take years of cross-checking with missions like Euclid and Roman in the future to see if these trends hold true for bigger groups of data. Dark radiation clues. The James Webb Space Telescope looks further back in time every time it goes into space, but the world gets weirder as you peel back more layers of time. Webb has found something unseen that acts like light, but isn't light. It's one of his quieter but most important discoveries so far. It's neither normal matter nor dark matter. It's somewhere in the middle, a faint, ghostly background of energy that cosmologists now call dark radiation. The term isn't new. Physicists have speculated about dark radiation for years as a missing link between dark matter and dark energy. But Webb may be the first to actually see its effects. When the telescope's instruments measured the brightness and temperature of extremely distant galaxies, they found a slight but consistent excess of background flux, more photons than the standard cosmological model predicts. Even after accounting for stars, galaxies, dust, and known radiation fields, there was leftover light energy that shouldn't exist. Not enough to break physics, but enough to bend it. At first, many assumed this was just a calibration error, stray sunlight or reflection within Webb's mirrors. But multiple deep-field observations across different sky regions returned the same result: a uniform, low-level infrared glow too strong to be explained by anything known. More interestingly, the distribution of this glow doesn't match the patterns of intergalactic dust or faint galaxies. Instead, it follows the expansion pattern expected from relativistic particles, things that move at or near the speed of light, yet interact only weakly with normal matter. That's exactly what dark radiation would do. In physics, radiation simply means energy carried by particles that move at light speed. Ordinary radiation includes photons and neutrinos, the latter being the most elusive known particles. But if other, unknown light-speed particles exist, they would add extra energy to the universe's early expansion. Even a tiny amount of this dark radiation could change how fast the cosmos grew, how early galaxies formed, and how the cosmic background cooled. This is where Webb's data becomes transformative. By comparing the inferred ages of the earliest galaxies with the timing predicted by the Lambda Cold Dark Matter (LCDM) model, astronomers noticed something curious. The galaxies seem too mature for the cosmic clock. Their development implies that the universe expanded faster in its early years than the standard model allows. One way to make that happen: add dark radiation. It would act as an extra push, a small but persistent pressure that accelerates the universe's early growth. Webb's findings align with an older mystery, the so-called effective number of neutrino species problem. Measurements of the cosmic microwave background from Planck and earlier satellites hinted at slightly more radiation energy than accounted for by the three known neutrino types. Cosmologists express this as an extra term, DNF, the amount of additional relativistic energy in the early universe. Webb's new data suggests that DNF might indeed be greater than zero, confirming that something other than photons and neutrinos contributed to the early cosmic heat bath. But what could that something be? The candidates are as exotic as they are fascinating. Some theorists propose a new kind of sterile neutrino, a heavier, non-interacting cousin of the known neutrinos that decays over cosmic time, leaving behind a faint radiation signature. Others point to the possibility of axions, hypothetical ultralight particles that could behave both as dark matter and as radiation depending on their energy state. Axions, if real, would also explain why some early galaxies rotate too slowly or exhibit unusual magnetic fields. Both features Webb has observed. Still, another crazy idea is that this dark radiation is left over from interuniversal leakage, which is energy leaking from nearby worlds in a multiverse with more dimensions. In the theory of brane cosmology, our universe is on a membrane floating in a mass with higher dimensions. When branes interact with each other, energy can be released that shows up in our universe as radiation. That background would look the same, stay the same, and be impossible to find, just like Webb's strange extra infrared glow. The matter-antimatter asymmetry re-examined. From what we know, the universe shouldn't be there. Every known physical rule says that the Big Bang should have created an equal amount of matter and antimatter. Antimatter is made up of particles that are mirror images of matter particles and destroy each other when they touch, giving off pure energy. We don't see that, though. Things in our world are mostly made of matter, and almost no antimatter. One of the biggest puzzles in astronomy is this imbalance, which is known as the matter-antimatter asymmetry. For many years, scientists thought the problem was solved. They thought that the scales of the universe were tilted by a small quantum imbalance. But James Webb's sharp look into the early universe has made the case open again. Webb's observations suggest that this imbalance might not just be a random fluke of physics. It might be evidence of a deeper process, one that began before the Big Bang, or perhaps in dimensions we can't directly perceive. In other words, the dominance of matter over antimatter could be the universe's memory of a prior age. To understand why this is such a big deal, we need to revisit the standard explanation. According to theory, moments after the Big Bang, the universe was so hot and dense that energy constantly turned into particle-antiparticle pairs. For every electron, there was a positron. For every proton, an antiproton. When the universe cooled slightly, most of those pairs annihilated each other, leaving behind only photons, light. Yet somehow, for every billion annihilations, one extra particle of matter remained. That tiny excess, about 1 part in a billion, is everything we see today, all galaxies, stars, planets, and life. Physicists have long attributed this to baryogenesis, a hypothetical process in which small violations of symmetry and particle interactions allowed slightly more matter than antimatter to form. Experiments in particle accelerators have observed minor instances of CP violation, charge parity violation, where certain particles behave differently from their antimatter counterparts. But those effects are far too weak to explain the enormous cosmic imbalance. Something else, something much stronger, must have happened at the dawn of time. That's where Webb comes in. By observing the chemical and energetic makeup of the earliest galaxies, Webb allows scientists to test whether this asymmetry was already baked into the universe from its first moments. The telescope's spectroscopic data shows surprisingly uneven distributions of ionized hydrogen and helium, suggesting that the early universe may have had regions where matter and antimatter didn't fully cancel out, patches of unequal composition that survived the initial annihilation. These differences appear too large to be explained by standard baryogenesis alone. What's more fascinating is the fact that Webb is still picking up weak infrared background light, which could contain signs of those old explosions. Gamma rays and photons are released when matter and antimatter hit each other. These photons would reach into the infrared range as the universe grew bigger. This is exactly where Webb is most sensitive. However, the telescope sees more of this diffuse glow than the models suggest. This suggests that the destruction may have happened on bigger, more organized scales, or over more than one epoch. One hypothesis gaining traction is that the matter-antimatter imbalance was inherited from a prior cosmic phase. In a cyclic or bounce cosmology, where universes collapse and re-expand endlessly, the dying phase of one universe could transfer its imbalance into the next. During the collapse, extreme gravitational conditions could segregate matter and antimatter into different regions, with one type favored in the subsequent expansion. If true, it would mean that our universe's matter dominance isn't a quirk of chance. It's part of a repeating cosmic rhythm. Another idea stems from brane world scenarios in string theory. If our universe is a 3D membrane floating in a higher dimensional bulk, it's possible that matter and antimatter were created on adjacent branes. They would then evolve separately, with only matter remaining in ours. Some theorists even propose that what we perceive as dark matter could actually be antimatter residing in a parallel brane, gravitationally coupled but otherwise invisible. In that case, the matter-antimatter balance might be perfect when viewed across the entire higher dimensional structure. It only appears lopsided within our limited slice of reality. Webb's data also challenge another long-standing assumption, that antimatter vanished completely after annihilation. The telescope has observed subtle spectral anomalies, tiny deviations in high-energy radiation from distant quasars, that some physicists interpret as signs of surviving antimatter clouds in intergalactic space. These wouldn't be massive enough to threaten cosmic stability, but their existence would indicate that annihilation wasn't total. A few isolated regions of antimatter might still exist, drifting silently between galaxies, invisible except through their faint gamma-ray echoes. Everyone in the field of physics is affected by these results. It would be like building a bridge between cycles of time if matter's control came from an asymmetry in the world that was already there. It also means that the mismatch between matter and antimatter could shape time's arrow, which points from the past to the future. Time might move in the opposite direction in worlds where antimatter rules, which fits with the idea of CPT symmetric cosmology. Quantum memory of the cosmos. The James Webb Space Telescope picks up light from a galaxy billions of light-years away. It also picks up a quantum message, which is an old message. Every photon that gets to Webb's mirrors has traveled unimaginable lengths and epochs, going through a universe that has grown, shrunk, and changed a million times. In some way, though, that photon still knows exactly where and when it was born. The world seems to have a memory that is not stored in words or matter, but in the language of quantum physics. More and more cosmologists think that this quantum memory could explain why Webb keeps finding signs of a world that existed before the Big Bang. The notion sounds mystical, but it arises naturally from physics. In quantum theory, information can't be destroyed. Whether an atom decays, a star explodes, or a black hole evaporates, the information about its original state must remain somewhere, preserved in the correlations between particles or in the structure of spacetime itself. This principle, called quantum unitarity, lies at the core of modern physics. Yet, if it's true, then the Big Bang, the supposed origin of everything, couldn't have been a clean reset. Some form of information from before that event must have survived. Webb's observations are pushing that idea from speculation to evidence. When the telescope peers into the early universe, it finds systems that behave as though they remember something. Galaxies that are too orderly, black holes that are too massive, and chemical ratios that imply a previous round of stellar evolution. It's as though the laws of physics didn't start from zero, but inherited instructions from a prior cosmic state. Quantum memory could be the mechanism by which that inheritance occurs. In simple terms, think of the universe as a vast quantum computer. Every interaction, every exchange of energy, every movement of a particle encodes data into the fabric of space-time. Over time, that data doesn't vanish, it diffuses. Even if the universe collapses or undergoes a bounce, the underlying quantum information remains imprinted in its geometry. When a new expansion begins, that information reboots, shaping the physical constants, matter distribution, and even quantum fluctuations of the next cosmos. Webb's discovery of early, mature structure could be direct evidence of that reboot, the universe recalling its last cycle. This idea gained traction after the black hole information paradox. For decades, scientists debated whether information falling into a black hole was lost forever. Recent work in holographic physics and string theory, especially the ADS-CFT correspondence, suggests it isn't. Information is preserved on the boundary of spacetime, projected like a hologram. That realization led physicists like Leonard Susskind and Juan Maldacena to a provocative conclusion. The entire universe could function as a holographic memory system. In that view, what we perceive as three-dimensional reality is an encoded projection of two-dimensional quantum data residing on the cosmic boundary, the horizon of our universe. If that's the case, then when the Big Bang occurred, it didn't erase the cosmic hard drive. It simply reinitialized it, rewriting over older information while leaving faint traces behind. Webb's ultra-deep observations of the cosmic background may be glimpsing those traces. Tiny anisotropies, non-random alignments, and frequency correlations that hint at pre-existing quantum structure. The early universe's uniformity, often cited as proof of inflation, might actually reflect inherited coherence from a previous quantum state. Entanglement adds another piece to the picture. In ways that are hard for traditional logic to understand, quantum entanglement connects objects in space and time. Experiments have shown that once two particles are entangled, they stay connected even if they are very far apart. Some cosmologists now think that whole parts of the universe may have been connected before the Big Bang, and that these connections have lasted into our time in the universe. If this is true, it would explain why the world looks so well-balanced and logical on a big scale. The quantum links that held the first universe together might still be forming the second one. Webb's detailed measurements of cosmic structure hint at exactly this kind of coherence. The early galaxies it observes seem to align or spin in subtle, correlated ways across immense distances, too consistent to be random. These patterns might represent residual quantum entanglement imprinted on matter during the universe's birth. In that sense, Webb is not just photographing distant galaxies, it's mapping the quantum memory field of reality. If quantum information can persist across cosmic transitions, then the universe may be part of a continuous informational chain, each cycle inheriting the data of the last. That would mean the constants of physics, the density of matter, and even the tendency for galaxies to form could be the output of a cosmic feedback loop. Universes might evolve informationally, refining their properties over endless cycles, converging toward configurations that allow structure, and eventually, observers like us. This vision transforms cosmology from a story of explosions and voids into one of computation and continuity. Every atom, every photon Webb detects, could be a bit of ancient data, recycled through the universe's memory system. The Big Bang would then mark not a beginning, but a data transfer, the moment the code of a prior universe was compiled into a new one. The thermodynamic mirror universe. Astronomers thought that the first pictures that the James Webb Space Telescope sent back of galaxies that were made less than 400 million years after the Big Bang would show a lot of chaos, with gas clouds and stars that were only partially formed. Structure, harmony, and balance were what they saw instead. It looked like the universe, which was still very young, had already reached a state of thermodynamic balance a lot faster than science would allow. The strange order brought back to life one of the weirdest and mathematically most logical ideas in modern cosmology, the mirror universe theory. This is the idea that there is a twin universe on the other side of time that follows the same rules but flows backwards in time. This theory begins with a problem as old as physics itself, the arrow of time. Every physical law from Newton's motion to Schrödinger's quantum equations is time-symmetric. They work just as well if you reverse the flow of time. Yet, in reality, we experience a forward direction. Entropy increases, eggs break, stars burn out. So where does that arrow come from? One explanation is that our universe started in an extraordinarily low entropy state, a condition of extreme order that has been degrading ever since. But why was it so ordered in the first place? In 2014, physicists Julian Barber, Tim Kozlowski, and Flavio Mercati proposed an elegant answer. Perhaps entropy increases in both directions away from a central Janus point. In their model, the Big Bang was not a singular beginning, but a symmetry point, the moment of lowest entropy between two expanding universes. On one side, time flows forward, ours. On the other, it flows backward, producing a mirror universe where entropy also increases relative to its own arrow of time. Both universes share the same physical laws and originate from the same event, but evolve in opposite temporal directions. If that sounds vague, Webb's discoveries may be putting it in a physical framework. The pictures from the telescope show that galaxies are forming earlier, faster, and more steadily than what normal cosmology says should happen. The way they are organized means that things were almost perfectly ordered at the start, which is exactly what a Janus point model needs. The early universe wasn't a mess, it was balanced. However, that symmetry might still be present in the very nature of spacetime. In the mirror universe framework, the Big Bang wasn't an explosion, but a bifurcation, a splitting of space-time into two time-oriented halves. Both began with identical conditions, but diverged thermodynamically. In our half, time moves forward, in the other, backward. From our perspective, that mirror cosmos would appear to evolve in reverse, galaxies contracting instead of expanding, light blue shifting instead of red shifting, entropy decreasing instead of increasing. But from within that universe, its inhabitants would perceive their own arrow of time as normal. Quantum theory predicts that such mirror universes would remain entangled across the Janus point. Information, energy, and even particles could remain correlated between the two sides. Some physicists believe this connection might explain several cosmological puzzles Webb has highlighted, including dark matter. In this interpretation, what we call dark matter could actually be mirror matter, ordinary matter existing in the time-reversed universe, gravitationally influencing ours through the shared geometry of space-time. It would explain why dark matter interacts only via gravity and why its distribution seems to mirror that of visible matter so precisely. Webb's deep field surveys have found several unexplained gravitational anomalies, regions where light bends as if mass were present, yet no visible source exists. These could be the footprints of matter existing behind our time horizon, the gravitational shadow of the mirror universe. Some simulations even show that such coupling would naturally stabilize galactic formation, providing exactly the kind of early cosmic order Webb observes. The consequences for thermodynamics are just as important. In both worlds, entropy moves away from a central point. This means that the Big Bang wasn't a state of endless chaos, but of perfect balance. Each world is the thermodynamic counterpart of the other, and they work together to keep things balanced, even though time flows in only one direction in some places. The arrow of time isn't basic in this way, it's social. Only the direction away from the Janus point is forward or backward in a general sense. Some observational signatures of this theory may already be within Webb's reach. The transition between universes would leave a subtle polarization pattern in the cosmic background light, a mirror-symmetric alignment of photon spin directions. Early analysis of Webb's infrared background data has hinted at such symmetry, though it's still too faint to confirm. Another test lies in neutrino physics. If mirror matter exists, there should be mirror neutrinos, identical but right-handed counterparts to our left-handed ones. Webb can't detect neutrinos directly, but it can measure their cosmological effects. A higher than expected neutrino density, or unexplained dark radiation, could be indirect evidence of mirror sector interactions, exactly what Webb's latest findings suggest. The mirror universe model also offers a new way to think about cosmic beginnings. Instead of a single arrow of time starting from nothing, we have a balanced pair of universes expanding in opposite directions from a shared birth. To an observer outside both, there is no preferred direction, only a timeless whole. From within, each universe experiences its own history, its own future, and never meets its twin again. The broken symmetry of light. Light has always been our guide. Photons have been telling the story of creation for billions of years, ever since the universe became clear. Galileo's simple lenses and James Webb's gold screens are just two examples of telescopes that have been made over the years. One can read those messages. Webb has shown, though, that light's story might not be entirely true. It is beautiful, but it has a flaw. A small broken symmetry that might explain why the universe looks organized, uneven, and maybe even older than it should be. To understand the problem, consider that the laws of physics treat light as perfectly symmetrical. Photons, the carriers of electromagnetic force, should obey strict conservation rules of energy, spin, and parity. The universe, in its earliest moments, should have produced radiation that was uniform and directionless. But when Webb began mapping light from the earliest galaxies and the faint glow that fills intergalactic space, it detected something unexpected, a preferred direction. This discovery builds on older hints from the Planck and WMAP satellites, which found tiny asymmetries in the polarization of the cosmic microwave background, patterns that appeared slightly twisted, as if light itself had a bias. Webb's sharper infrared data has confirmed that these asymmetries persist at later epochs and higher energies. In simpler terms, some cosmic light appears to favor one-handedness over the other, a phenomenon known as parity violation. In physics, parity symmetry means the universe should look the same if viewed in a mirror. If you flip left and right, or forward and backward, the fundamental laws shouldn't change. Yet light, particularly polarized light, seems to defy this principle. Certain photons twist one way more often than the other, suggesting the universe itself has a handedness. That's extraordinary, because electromagnetism, in theory, should be neutral. Only the weak nuclear force is known to violate parity. So why is light, the purest, most universal messenger, showing the same kind of bias? Webb's observations point to two possible answers, both extraordinary. The first is that light's asymmetry is a relic from the very beginning, or from before it. If the Big Bang was not a singular origin but a transition from a prior universe, the quantum fields responsible for creating photons may have retained a directional imprint. This could happen if the previous universe had a dominant magnetic polarity or a large-scale rotation. When our universe bounced into existence, those conditions could have imprinted a small but persistent twist on all future light. In that case, every photon Webb detects carries a fingerprint from a time older than time, a subtle memory of the universe's previous spin. The second possibility is that this symmetry breaking isn't ancient, but ongoing. Some theorists propose that space itself is not perfectly uniform, but filled with a hidden field that slightly modifies the behavior of photons over great distances. This hypothetical field, sometimes called an axion field, could cause light to rotate as it travels, slowly twisting its polarization over billions of light years. Such a process, known as cosmic birefringence, would make light from distant galaxies appear polarized in one direction more than another. Webb's high-resolution infrared polarimetry has detected precisely this effect, too strong to be explained by interstellar dust alone. If real, axion-induced birefringence would be one of the first direct hints of new physics beyond the standard model. Axions were originally proposed to explain why the strong nuclear force respects parity when it theoretically shouldn't, but they've since become leading candidates for dark matter. If the early universe was saturated with these particles, they could subtly twist light as it passed through them, breaking symmetry and leaving behind the directional signal Webb now observes. There's more to the answer than meets the eye. Asymmetry in light might have something to do with the fact that time is not always the same for everyone. If the universe has two sides, like in the mirror universe or Janus model, light passing through the line where the two halves of time meet could experience a small phase shift, which would change the direction of its polarization. Over very long distances in space, the combined effect would show up as a preferred direction in the polarization of very old photons. By noticing that slight difference, Webb may have caught a glimpse of the line where two different timelines meet. That would mean light isn't just carrying information about space, it's carrying information about time's architecture itself. The broken symmetry also aligns with Webb's detection of galaxies that rotate in consistent orientations across enormous scales. If the early universe had even a slight twist, a cosmic vorticity, it could have polarized the radiation field, seeded angular momentum in forming galaxies, and produced the large-scale spin patterns Webb now sees. Such alignment would once have been dismissed as coincidence, but it's appearing too often in too many data sets to ignore. When constants change. The so-called fundamental constants are a set of numbers that can't be changed. The fundamental constants of physics that control electromagnetic interactions, the speed of light, and the charge of an electron make up the cosmic base. Life would not be possible if even one of them were slightly different. Stars would not form, atoms would not stay together, and stars would not form. Scientists thought these factors were always the same for 100 years. From what the James Webb Space Telescope can see, though, those numbers might not be set in stone after all in the farthest reaches of space and time. The idea that the laws of physics could vary sounds heretical, yet it has precedent. In the 1930s, physicist Paul Dirac speculated that some cosmic parameters might evolve as the universe expands. Later, astronomers began testing that idea by examining the fine structure constant, often called alpha. It's a dimensionless number, approximately 1/137th, that determines how strongly light interacts with matter. A larger alpha would make atoms bind tighter and shift spectral lines slightly. A smaller one would loosen those bonds. Even a change of a few parts per million would be detectable in the light from distant galaxies. Webb's spectroscopic precision is finally sensitive enough to test this idea on a truly cosmic scale, and the early results are unsettling. When Webb analyzed absorption lines from galaxies more than 12 billion light-years away, it found that the positions of those lines don't perfectly match laboratory values. The shifts are tiny, fractions of an angstrom, but statistically significant. If the data hold, it means the fine structure constant may have been slightly smaller in the early universe. If true, that would mean the strength of electromagnetism, and by extension, the behavior of all atoms, has changed over time. Light would have interacted differently with matter billions of years ago, altering how stars burned, how molecules formed, and how radiation cooled. Such a variation could help explain why Webb sees galaxies evolving faster than expected. Their atomic and molecular processes might have run under subtly different rules. The implications ripple outward. If one constant can vary, perhaps others can too. Some cosmologists propose that as the universe expands, the values of fundamental parameters evolve along with its geometry, a natural consequence of higher dimensional physics. In brane world models, where our universe is a three-dimensional surface embedded in a higher dimensional space, the constants we observe may depend on how our brain moves or vibrates within that bulk. As the geometry shifts, so do the apparent strengths of forces. From this perspective, the changing constants aren't random. They're the shadow of a dynamic higher dimensional reality. The constants might change across space instead of time, which is also an appealing option. Our observable area might be close to the edge of two different domains if the universe is part of a multiverse and each pocket universe has slightly different physical rules. Constants would change across those lines, first in a way that couldn't be seen, and then more obviously at very long distances. Webb's findings of spectral anomalies that are clustered in certain sky directions may be the first proof of this kind of gradient. Also, that might explain why one side of the universe seems to be expanding a little faster than the other, as if it's in slightly different physical conditions. This is something that can be seen in both Webb and Planck data. If constants truly drift, it could also solve the persistent Hubble tension, the discrepancy between the local and early universe expansion rates. A tiny change in the gravitational constant or fine structure constant over time would alter how we interpret both sets of measurements, potentially reconciling them without new physics. In that case, the universe's laws themselves would be evolving, self-correcting, as it ages. Of course, extraordinary claims demand extraordinary verification. Webb's spectral lines could be influenced by intervening gas clouds, motion effects, or instrumental calibration errors. Astronomers are now cross-checking with the Atacama Large Millimeter Sub-Millimeter Array, ALMA, and the upcoming Extremely Large Telescope, ELT, to confirm whether the same shifts appear in other datasets. If independent observatories detect the same pattern, it would mark one of the most transformative discoveries in modern science, that the laws of physics are not timeless. But suppose Webb's data are right. Suppose constants do change, even slightly. What then? The philosophical shock would be immense. It would mean the laws of nature are not eternal edicts, but evolving relationships. The universe wouldn't be a machine running on fixed rules. It would be a living system, changing its own code as it unfolds. Each cosmic era could operate under subtly different physics, perhaps even allowing conditions that once made formation easier, and that may fade away over time. The quantum memory hypothesis seems to fit very well with this idea. If data is never lost, then the constants we measure could store the knowledge of all the cycles that came before. Each universe would take on the physical properties of its parent, with quantum fluctuations during restart possibly making small changes. So, the fine structure constants shift wouldn't be a break in natural law. It would be the law itself changing over time. Echoes from before inflation. Cosmological inflation, an exponential burst of expansion that smoothed out the chaos of the Big Bang, is thought to have happened long before the first stars burned, before even atoms or light existed. It was an incredibly short and violent event. This idea has been an important part of current astronomy for many years. The cosmic microwave background is so smooth, and space itself seems flat. This is why the universe looks so regular. Now, though, the James Webb Space Telescope is quietly calling that picture into question. Its deep-field pictures suggest that there may be echoes, which are faint, long-lasting patterns in the structure of the universe that may not have come from inflation, but from something that was there before it. Inflation theory says that all traces of pre-Big Bang conditions were wiped clean by expansion. The universe, stretched faster than light, lost any memory of what came before. Everything we observe today, galaxies, clusters, even the largest voids, should be the result of quantum fluctuations, magnified during that inflationary growth. Yet Webb's observations suggest a more complicated story. When astronomers map the distribution of the earliest galaxies, they find a repeating rhythm, a slight oscillation in the spacing between large clusters and voids. These baryon acoustic oscillations should be random, but Webb's ultra-precise measurements show subtle correlations at unexpected scales, as if the universe inherited a faint vibration from a time before inflation even began. Some cosmologists call these signals pre-inflationary echoes, fingerprints of physical processes that occurred in a parent cosmos. In this view, inflation wasn't the beginning but a bridge, a phase transition between two states of reality. If a previous universe collapsed or transformed into ours, the quantum fields governing that event could have left imprints in spacetime, ripples in density, pressure, or geometry, that inflation didn't fully erase. These echoes would appear today as faint, large-scale anomalies in galaxy clustering, cosmic background radiation, and even polarization patterns. Webb, with its unrivaled resolution, is starting to see those patterns more clearly than ever before. Webb's mapping of cosmic filaments, the huge strings of matter that connect galaxies across the universe, is an amazing illustration. Simulations based on theory suggest a random structure that looks like a web. The data from Webb, on the other hand, show something more organized, filaments that were oriented at regular times, hundreds of millions of light-years apart. The math is too well organized for it to have come about just because of changes in inflation. It's like the universe had a structure pre-tuned with it before it expanded and made it into the cosmic web we see today. A similar anomaly shows up in the faint infrared background, the diffuse glow filling the space between galaxies. Webb detects subtle modulations in that background's intensity, oscillations that repeat over large angular scales. These cannot be explained by known astrophysical sources or by random noise. Instead, they could represent standing waves in spacetime, fossil vibrations left over from an earlier cosmic cycle. Inflation should have smoothed such vibrations into oblivion. The fact that Webb sees them at all suggests inflation either wasn't long enough, or it didn't erase the memory of what came before. Physicists exploring this possibility often turn to loop quantum cosmology, or bounce models, where the universe's expansion arises from the rebound of a prior contraction. In these models, when a collapsing universe reaches Planck scale density, quantum effects prevent a singularity. Instead, gravity becomes repulsive, triggering a new expansion. The transition creates a bounce, during which density waves from the collapsing phase carry through into the expanding one. Those waves would appear today as the very echoes Webb may be detecting. Other explanations reach even deeper into speculative physics. Some versions of string theory propose that our universe formed from the collision of higher dimensional membranes, or branes, floating in a multidimensional bulk. The violent impact would have triggered inflation in both branes, but the pre-collision vibrations of those membranes, their quantum tremors, could still linger, encoded in spacetime's curvature. Webb's detection of slightly repetitive density patterns in galaxy distribution fits this picture almost perfectly. If these echoes are real, they could be the key to unifying cosmology's great divide, the gap between quantum physics and general relativity. The very existence of pre-inflationary memory implies that quantum effects governed spacetime itself before classical expansion began. It means the seeds of today's structure were planted not by random inflationary noise, but by coherent quantum processes, perhaps even by the death throes of a universe before ours. The data are also notably in line with studies into gravitational waves. Recently, pulsar timing arrays found a weak, low-frequency gravitational hum that could be the same kind of relic, waves from before inflation made stronger by the expansion of the universe. As long as Webb's spatial echoes match those temporal ones, they might show different sides of the same thing: space-time, remembering how it looked before. The universe before the universe. The James Webb Space Telescope was made to look back to the beginning of time. But what if the beginning wasn't how we thought it was? What if the Big Bang wasn't the start of the universe, but rather a doorway into a universe that was already there in some form before ours? That idea, which was once on the very edge of theory, is now at the center of the bravest discussions in astronomy. And Webb, with its gold screens and infrared eyes, may be the tool that finally makes us accept it. The evidence has been building piece by piece. Mature galaxies appeared when the universe should have been in its infancy. Massive black holes are already weighing billions of suns just a few 100 million years after the supposed beginning. Heavy elements, carbon, oxygen, iron, existed too soon to have been forged by the first stars. Even the faint glow that fills the cosmic dark, the ghost light, appears too structured, too uniform, to come solely from our era of creation. Each of these discoveries by Webb seems to whisper the same message: something was already here. To understand what before the universe could mean, we must let go of the word before. Time, as we know it, began with the Big Bang. Asking what came before is like asking what lies north of the North Pole. Yet modern physics gives us tools to think beyond that metaphor. In quantum cosmology and loop gravity models, time is not absolute. It's emergent, arising from the relationships between things. When space-time reaches extreme density, those relationships break down, and before and after become meaningless. But that doesn't mean nothing existed, only that what existed didn't experience time the way we do. In that timeless realm, the universe could have been a quantum state, a field of potential, oscillating between existence and non-existence. Fluctuations within that field might have triggered what we perceive as the Big Bang, not a creation ex nihilo, but a phase transition, a moment when latent energy crystallized into the dimensions of space and time. In this scenario, the universe didn't start, it changed state. And if so, our Big Bang wasn't unique. Countless such transitions may have occurred, before elsewhere and perhaps even again. Some cosmologists go even further and imagine a multiverse of loops that will never end. One version says that worlds grow, cool down, and fade away into a smooth radiation. They are then reborn when quantum changes cause new bubbles of space-time to form. In another, worlds fall apart into black holes that lead to new realities. Each singularity is like a womb where new things are born. The traces of those other worlds might still be visible in ours as patterns, such as gravity signatures, chemical imbalances, or tiny quantum connections. Webb's observations of early structure including its strange order and old materials, may have made those fingerprints clear. Roger Penrose's conformal cyclic cosmology offers one of the most elegant pictures of this idea. In his model, as the previous universe expands indefinitely, all matter decays and only radiation remains. Without mass, there's no way to distinguish time or scale. The universe becomes conformally smooth. At that point, it mathematically resembles the state of a new Big Bang. One universe's infinite future becomes the next's instant beginning. Penrose even predicted faint circular patterns in the cosmic background, Hawking points, from the evaporation of black holes in the previous eon. Webb's ultra-sensitive detectors have begun to see unexplained ring-like features in the infrared background that could be exactly that, echoes from the death throes of an older cosmos. Other physicists approach the question from quantum mechanics itself. If information can't be destroyed, then the quantum data from any prior universe must persist, encoded in the vacuum. The Big Bang, then, was not a blank slate, but a rewrite, a new layer on an old hard drive. That's why Webb's observations show a universe that looks too experienced for its age. It's not young matter, but recycled memory. Every atom we study, every photon we detect, may contain information from an existence that collapsed long before ours began. If universes emerge endlessly, one from another, what sustains the process? Why should there be something rather than nothing, again and again? Some theorists suggest that nothingness isn't empty at all, but inherently unstable, overflowing with quantum potential. Existence, in that view, isn't created. It's inevitable. Reality is what the vacuum does when it can't stay still. The philosophical weight of that idea is immense. It means that creation is not a singular miracle, but a natural rhythm, the cosmos breathing in and out forever. Each universe, including ours, inherits the ashes and wisdom of the last. Every expansion is both a beginning and an echo, each collapse both an ending and a seed. And through instruments like Webb, for the first time, we can glimpse that rhythm written in light. The James Webb Space Telescope may not have found the start of everything, but it did find proof that the universe will never really start. Every light Webb sees is a memory, and every galaxy is a new chapter in an old story that is still being told. Have you been as amazed by that idea as we were? If so, please like this video, follow for more discoveries in deep space, and watch the next video you see.